RAFM 2020, organized by the Department of Physics in collaboration with the Star College Scheme of Department of Biotechnology, DBT, Government of India, and under the aegis of the Internal Quality Assurance Cell of Atma Sanatan College. It gives me immense pleasure to welcome our distinguished guests on the occasion. Professor Pradeep Kumar Verma, Chairman, College Governing Body, and Professor in the Department of Genetics, University of Delhi. Chief guest of this national seminar. Sir, we are really honored to have you with us. It's my great pleasure and honor to welcome our guest of honor, Professor Prem Lal Unyal, Treasurer, College Governing Body, and Professor in the Department of Botany, University of Delhi. On behalf of IQAC and the Department of Physics of ARSD College, I welcome Professor Vinay Gupta, Professor in the Department of Physics and Astrophysics, University of Delhi, and keynote speaker of this conference. I also welcome our Principal, Dr. Gyantosh Kumar Jha, and thank him for his constant support. And sir, without your guidance and encouragement and positive support, this national conference wouldn't have been possible. Now I invite the principal of the college to welcome our guests and say a few words on this occasion.
Thank you, Vinita. Honorable Professor Pradeep Verma ji, Chairman, College Governing Body and Chief Guest of this function, inaugural function. Professor Prem Lal Unyal ji, Treasurer of College Governing Body and Guest of Honor. Professor Vinay Gupta ji, today's keynote speaker for this session. Dr. Vinita Tuli, convener of this conference. Dr. Manish Kumar, co-convener for this conference. Other colleagues, dear participants, and my dear students. On behalf of Atma Sanatan College, it's a great pleasure and honor for me to welcome you all in this conference organized by Physics Department under the aegis of Internal Quality Assurance Cell of the college and DBT Star College Scheme. I would like to congratulate the Physics Department for organizing two-day online national conference on recent advances in functional materials. In fact, we have research-oriented faculty members in the Department of Physics. Many research projects are running in the Department of Physics, awarded from different government agencies such as DST, UGC, CSIR, DBT, and BNRS, etc. Many undergraduate and project students are involved in different ongoing in-house and innovation projects and published research papers in international journals of repute during their course. Faculty members published more than 150 research papers in the last 1 year and approx 50 research papers during this pandemic situation. Apart from this, our physics department is constantly organizing different academic and scientific activities in the college. This is the third national conference in the last 3 years. This conference is focused on recent advancement in the functional materials. Functional materials are the key for the future materials based on technology. I am extending the best wishes for the organizing committee for planning this online national conference. Once again, I would like to welcome all the dignitaries, guests in this conference, all the participants, and my best wishes to the organizing team, especially Dr. Vinita Tuli and Dr. Manish Kumar, all the secretaries who are involved for this organization. Thank you so much. Over to you.
Yes. Thank you, sir. Atma Sanatan College, a co-educational constituent college of the University of Delhi, was founded on 3rd August 1959 by the Sanatan Sabha based in Delhi. It aims to nurture excellence in education. The college embraces inclusivity and equitability as its founding principles. The college is concerned primarily with creating an institution in tune with contemporary demands and enabling the holistic development of all its stakeholders. Its emphasis on undergraduate research, entrepreneurial initiatives, skill development, strong industry institution linkages, and ICT-enabled learning environment are geared towards the facilitation of sustainable and self-sufficient systems. The motto of the college, Tejasvi Nagdhitamastu, has been taken from the Taittiriya Upanishad and means, may our learning be endowed. The college has seen an exponential growth over the past few years under the leadership of our dynamic principal, Dr. Gyantosh Kumar Jha. The college is accredited grade A by NAC and was 5th in NIRF rankings in 2017 and 14th in 2018 and 2019, and 13th rank in the recently released rankings in the year 2020 by the MHRD, now the Ministry of Education. Our department is one of the 4 departments who have benefited under the Star College scheme of DBT. Other departments are chemistry, mathematics, and life sciences. The main aim of the scheme is to popularize science. Till date, we have completed 52 in-house projects under this scheme, and around 300 students have benefited from it. The college activities under this scheme are regular field visits of students, hands-on training of different softwares for students and the non-teaching staff, seminars, conferences, and FDPs, which are held on regular basis. This is the 3rd national conference which the physics department is organizing under this scheme and under the aegis of the Internal Quality Assurance Cell of the college. We have also organized under this scheme free health checkup camps for teaching, non-teaching staff and students of the college, and students of the schools are invited regularly and given exposure to lab facilities which they are lacking in their schools. And now I invite Dr. Manish Kumar, the teacher in charge of our department and the co-convener of this seminar and this conference, to give details about this conference.
Thank you, ma'am. Good morning to all. On behalf of the Department of Physics, Atma Sanatan Dharma College, I, Manish Kumar, Coordinator Department of Physics, welcome to all participants and delegates who will join this 2 days national online national conference on recent advances in functional materials, RAFM 2020. Our department is devoted with many young and dynamic faculty members. Those are constantly involved in the innovative research work. We are trying to do our best to contribute significantly for our college and society. We have planned to organize this national conference through online mode in this pandemic situation for the enrichment and benefit of the material research society of the nation and world. Functional materials, if we are talking about the this conference theme, functional materials, the functional materials are effectively being utilized in a massive area of human development through several technologies. In the light of the enormous advancement and potential use in various applications of functional materials, international and national conferences have been organized to bring together scientists, researchers, faculty, as well as experts from industries with collective interests to discuss the recent advancement of multifunctional materials. In the same effort, we are inviting you to the National Conference on Recent Advances in Functional Materials. Still, the entire world is stuck due to the spread of COVID-19 and people are bound to stay home. But apart from it, the scientific personality and innovation know no limits and boundaries. Therefore, we have decided to organize RAFM 2020 through online mode. It is supposed that this conference will be a novel, exciting, and learning experience for all of us. The conference will cover a wide range of topics like multifunctional materials, biomaterials, DFT and DFT density functional theory and solar simulation of materials, perovskite and double perovskite materials, luminescent materials, smart materials, materials for energy conversion and storage. Smart materials, advanced functional materials, materials in agriculture, polymeric materials, composites, liquid crystals, materials for sustainable development, nanomaterials and thin films, smart devices and quantum dots, synthesis technique and characterization tools with application in smart devices. I'm sure that the conference will promote the awareness of the state of art of the material science and will prove to be an excellent forum for starting interdisciplinary collaborative research work in material science across the country. I wish for every success of this 2 days national conference. Thank you all. Thank you. Thank you, ma'am.
Thank you, Manish. I once again welcome Professor Premlal Unial, Treasurer, College Governing Body and Professor in the Department of Botany, University of Delhi, and guest of honor on this occasion. Professor Unial did his PhD from the Punjab University, Chandigarh. He joined the Department of Botany, University of Delhi as a research associate in the year 1992 and became a professor in the same department in the year 2009. He has supervised and guided 8 students for PhD degree and 22 for MPhil degree. Professor Unial has 17 publications in reputed international journals. I invite Professor Unial to say a few words of encouragement to all of us.
Sir, please unmute, sir. Thank you.
Thank you, Vinita. It is a great pleasure to me to be the part of this grand academic event. I would like to refer one thing that reaching to the high ranking by the college, it is due to the outstanding performance by the teachers as well as the principals, means in the teaching activity, research activities, administrative activities, extracurricular activities. Really, the college gained a very good position in the ranking. And I think the college teachers, principals, students, and other staff deserve a great appreciation. Regarding this conference organized by the physics department, it is a really great it's always have been a very beneficial to have a conference where the academicians, students, teachers, they interact with each other, share the knowledge, and which really benefit the academic career of all of us. In fact, I am not a physics man, but really many of the aspects are used in the plant sciences, and we cannot go without physics. So combining the various subjects, doing research, bringing innovations in the academics, it's a great thing. And I am definitely sure that this conference will be a memorable event in the history of this Atma Sanatan Dharma College, and all of us, we will get benefited. Thank you very much.
Thank you so much, sir. I once again welcome Professor Pradeep Kumar Burma, Chairman, College Governing Body and Professor in the Department of Genetics, University of Delhi, and the chief guest on this occasion. Professor Burma did his BSc, MSc, and PhD from the Banaras Hindu University and joined the Department of Genetics as professor in the year 2009. Professor Burma has held many administrative assignments as well. He is the Dean Faculty of Interdisciplinary and Applied Sciences, and Professor Burma has been the Head Department of Genetics, Head Department of Biophysics, Head Department of Physical Education, and also Joint Proctor, University of Delhi. Professor Burma has also been the Chairman, Governing Body of Gargi College, University of Delhi. He has supervised 14 students and they have been awarded PhD degree under his guidance, and also 4 students for their MPhil degree. Professor Burma has 46 research papers published in international journals of repute and 5 patents to his credit. I invite you, sir, to say a few words of encouragement.
Firstly, let me welcome all of you on behalf of the college, as well as also on my personal behalf, this 2-day conference that has been organized. In this time when there are a lot of virtual meetings that is happening, it's nice to see that the spirits are up, and we are going to have a pretty intense discussion. I looked at the schedule and I found there are a lot of presentations and so on. And I really, this is, I think, also congratulate the organizers to get all this together. And of course, the principal, Dr. Jha, must have been behind this, always encouraging you all to do such activities. Going to the schedule, I was also very interested to, it was nice to see that you have a set of poster sessions which have been organized, and I'll join in to see that how a virtual poster session can be done, because even in our departments, we can do these webinars and talks, but we have never thought of doing a poster session for the students. So maybe it will be a good learning lesson also for me. I've been actually, it's a great privilege to have been become associated with this college, which has been doing extremely well over the years. And I think it's all the staff and the faculty and the students who have all built this whole thing up, which also reflects in the kind of workshops that are and conferences and talks that are being organized by this college, even during this period of COVID and so on, lockdowns and so on. I wish the organizers all the best for these next 2 days, and I'm sure all the participants will enjoy the talks. And the first one, I think, starts with Professor Vinay Gupta, and I saw that there are some very interesting ones, though I'm not associated with this field at all, but there are some interesting talks which I think maybe I'll join in to listen to. One of them being that one was, I think, was on how knowledges and materials have led to current technologies and so on, which will be also a great learner thing for me to also learn from. So I welcome you all again, and I wish you all the best. And I'm sure you will all enjoy these 2-day intense discussions and presentations. Thank you.
Thank you, sir. And your words of encouragement, they mean a lot to us, sir. I am privileged to once again welcome Professor Vinay Gupta as our keynote speaker. Professor Vinay Gupta, serving as in the Department of Physics and Astrophysics, University of Delhi, as professor since 2004. His current research area includes semiconductor and surface acoustic wave sensors for gas, chemical, radiation, biomolecules, amperometric, photometric biosensors, surface plasmon resonance, technique for dielectric studies and sensing applications, microfluidics, nanostructured materials, piezoelectric and multiferroic thin films, ceramics for energy harvesting applications, pressure sensors, RF and microwave resonators, photonic devices, nonlinear optical devices, SAW devices, MEMS transducers and microheaters, molecular simulations and device modeling. He has developed electronic materials and devices laboratory, which is well equipped with high-end instruments like laser MBE, PLD, sputtering and device fabrication techniques, to name a few. His research group is internationally recognized, working in the techniques, to name a few. His research group working in the areas of processing and development of multifunctional electronic materials. He is engaged towards the development of integrated devices having strategic as well as commercial applications. His research group has successfully integrated piezoelectric zinc oxide thin films with MEMS structures fabricated by CIRI India for acoustic sensors as per specification designed by Indian Space Research Organization, ISRO. These acoustic sensors have been installed in PSLV flights of ISRO from C9 onwards. He has published more than 345 research papers in high impact factor SCI journals. He has been granted 1 US and 3 Indian patents along with 1 successful technology transfer of indigenously developed tabletop SPR system, which is being used in various academic and research institutes. He is an active member of various reputed research societies like IEEE, MRSI, EMSI, etc. At present, he has project grants of more than rupees 4 crores. He is recipient of MRSI Medal 2012 presented by the Material Research Society of India, and also recently received Distinguished Teachers Award by the University of Delhi. 2 days ago, one more feather is added to his cap when Stanford ranking of world's best scientists was announced, in which he ranked amongst the top 2% scientists. Congratulations to you, sir. Now I invite Professor Vinay Gupta for his lecture.
Thank you, Dr. Vanita. And respected Professor Pradeep Burma, Professor UL Unyal, Dr. Gyanutosh, my dear colleagues, research scholars, and students. So the talk, I'm audible?
Yes,
Hello.
sir.
Okay.
Yes, sir.
Yes, sir.
Yes, sir.
So the presentation of my talk is basically on multifunctional materials, nitride, and their heterostructures and quantum wells by laser MBE technique for shortwave photonic devices. So outline is where we have developed indigenously one laser MBE system in the department to grow the nitride film. And using this technique, we developed undoped and doped gallium nitride layers and their quantum wells for light emitting diodes, as well as fabrication of UV detectors. So what are the photonic devices? As you know, it links with the photons. So generation, detection, and manipulation of photons and their processing through various devices, which can be used for multifunctional applications like switching, modulators, amplification, sensors, and the components which are used to deal with the photons are basically the photonic devices. So as far as short wavelength is concerned, short wavelengths, we are talking about the visible light on the lower wavelength side. So it can start from blue, 450 nanometer to 470 nanometer, and violet, and then ultraviolet. And even we can go further deeper to the ultraviolet light. The key factor as well as photonic devices are concerned is that we need a direct band gap material where the bottom of conduction band and top of the valence band should be at the same momentum level at k equal to 0. And these materials leads to the radiative combinations of electron-hole pair, which leads to the emission of the photon, and which is very crucial for all photonic devices. And the band gap, which should be in the short wavelength, the ultraviolet or blue side, those materials are important for development of photonic devices. If we want a white light, for example, in this case, there are two mechanisms. One mechanism is that we can have blue LED or ultraviolet LED, and then we can coat some suitable phosphor on the top of that, and that phosphor is going to give the radiations over the entire spectra of the visible light, and we can generate the white light. As far as other possibilities that we can choose the 3 LEDs of green, blue, and red, and we can combine their color mixing. And by color mixing, we can generate the white light. As far as photodetector is concerned, where instead of generation, we are absorbing the photons and we are using to detect it. In this case, again, as I mentioned, that we are focusing on short wavelength region, and the photo emission, the property of the photodetector, which is based on photo emissions, is basically characterized in 3 parts: the bulk phenomena, Schottky diode, and PN junction. So here the bulk is not so good because the response time and recovery time is very, very small. So basically we are focusing on Schottky diode and PN junction diodes to make the UV photodetector. To make a photodetector, the important parameters are about their sensitivity should be good, response time should be good, they should be insensitive to the ambient conditions, cost should be less, and operating shelf life should be as large as possible. So to achieve all these, the photo detector as well as LEDs, the multifunctional material is nitride based material, and the basic compound is gallium nitride. So gallium nitride is here somewhere around band gap of around 3.4 electron volt, which is around ultraviolet light. Lambda is around 380 nanometer or 360 nanometer. And we can tailor this band gap by either alloying with the aluminum or by alloying with the indium. An entire spectrum of the short wavelength can be covered here by using the alloying with the aluminum as well as indium in the gallium nitride. And besides that, this material is very good as far as the stability is concerned in the thermal and chemical stability is concerned. The breakdown is very, very high and mobility is very good for this material. So these are some important parameters which I already mentioned you, that as far as the band gap is concerned, the band gap can be tuned from 3.4 electron volt to the 6.2 electron volt when aluminum is rich, and when indium is rich, it can go down up to the 0.7. So this is a very beautiful material where you can tune the conductivity, you can tune the band gap of this material, and you can choose what application you want for this material. However, to grow the nitride, there are some challenges which is very critical. And the basic challenge as far as nitride is concerned, to grow very good epitaxial film with minimal defects in the crystal structures of this material. So for that purpose, we need a basic substrate, a crystalline platform, which should have the low thermal expansion and minimum lattice mismatch. So this is very critical, and cost should be as low as possible and should be stable in nitrogen environment, because we have to grow the nitride film. And these are some suitable substrate where I'm just showing how much lattice mismatch is there. If lattice mismatch is less, we can grow a very good layer of gallium nitride. If lattice mismatch is very large, then it is difficult to grow gallium nitride with good quality. But on the other side, like the silicon carbide, for example, the cost is very, very high. Alternatively, one can choose another material, aluminum nitride, whose lattice mismatch is very less, in between high lattice mismatch substrate and the gallium nitride, so that you can reduce the lattice mismatch and you can grow gallium nitride film of very good quality. So for that purpose, there are some techniques which are established in the commercial market: MOCVD, HVPE, MBE. These are already, these techniques are there, and each technique has its own advantage and disadvantage. So what we have done at University of Delhi, we have developed one indigenous laser molecular beam epitaxy technique, or you can say ultra high vacuum pulse laser deposition systems, as an alternative approach to grow this nitride film. In this technique, we use a very high power laser, and we incident this high power laser, we focus that on the target of gallium nitride or any other solid surface. And then when they interact with this, localized heating is there, and this material eject out and comes out in the form of plume. And then we can deposit this material on some platform. We can use a specialized tool, the reed, which can see the crystallographic structure of the growing material in situ while growing, and we can see whether the material is growing perfectly or not, or what are the problem in this. The advantage with this technique is that we can deposit this material with a relatively low growth temperature, and there is no need to use the toxic gases which were used in previously mentioned commercial techniques, and post-depositional treatment is also not required. And in this technique, which we have developed at University of Delhi, this is the first equipment in the India which has been developed completely indigenously at Department of Physics. And in the vacuum level which we can reach here is around 10 to the power minus 10 to 10 to the power minus 11 torr. So that's the vacuum level which we can achieve. So we have filed the patent also on Indian patents, where we have developed an inverted light emitting diode by using the laser MB technique, a cost-effective technique, this one. So this is completely indigenous, which we have developed in the collaboration with an industry, Messrs. Excel in the Mumbai, Maharashtra. The silent feature of this technique, which we have developed here in the department, is that this still chamber is there, and this still chamber is bakeable. Why bakeable? Because we want to achieve the vacuum of the order of 10 to the power minus 11, 10 to the minus 10 torr. And for that purpose, we need to bake the chamber again and again. Also, all the pumps which are attached with these systems are oil-free. So there is no possibility of any contamination inside the chamber. So whatever material we are growing are almost contamination-free. And another beautiful thing with this system is that laser resting. That means we can tune this insert laser by rotating the mirror, and multiple beams can incident on the target, so that large area deposition is possible. With the PLD system, the restriction is about the area. Generally, we can deposit 1 centimeter by 1 centimeter film. By using this laser resting, it is possible to grow the film up to the 2-inch diameter with quite good uniformity. And then these are the other, you can say, the beneficial which we have attached with the system, where we have used the RF plasma cell. So we can incident the nitrogen, we can crack the nitrogen, decompose, and we can use these radicals, we can dissociate the nitrogens, and easily they can mix with gallium nitride and can grow the very good quality gallium nitride. So solid reaction can take place inside the chamber. Load block possibility is there, so that without breaking the vacuum in the main chamber, we can insert our sample, and the high level vacuum is maintained in the system. Also, we have the very good substrate assembly, the inverted one, the target holder assembly, where we can hold the 6 targets simultaneously. But the beauty in the system is that these targets can be in the liquid form or can be in the solid form, both. So we can deposit the film by using the liquid target or by using the solid target. So that's the added advantage with this one. So this is the technique which has been designed and already installed and working very beautifully from last several years in the department. So this is a complete system. So laser is here, excimer laser, very high power. And this is the guided path for the laser. Mirrors are there inside this platform. So laser goes like this and goes like this. Inside this is the chamber. And you can see the aluminum foil. Under the aluminum foil, there are a lot of tapes, heating tapes, which can be used to bake the chamber. And this laser light is going to incident inside the chamber and interact with the target, and substrate is on the top. So this is the top substrate assembly. This is the target assembly. So this is a completely controlled system for this laser MB systems, which is currently working at Department of Physics. Since we are working with the photonic devices, to make the photonic devices, we need the homojunctions, heterojunctions, as well as quantum wells. So what are the homojunctions? The homojunctions is a PN junction having the same material. So if we have silicon, on both the sides silicon is there, or we have gallium nitride on both the sides, gallium nitride. So one is N-type, one is P-type, and we can make the homojunction. As far as heterojunctions are concerned, then it should be 2 different materials, with one N-type, one P-type. If 2 different materials are there, their band gaps are different. So instead of the better aligned, you can say, because band gap is different, so they are treated as the heterojunctions. Quantum wells. A quantum well is basically interface of 2 different band gap materials. One is very large band gap, another is small band gap. So the small band gap act as the well where you can confine the charge carrier, and large band gap act as the barrier for this confined charge carrier. So this is a single quantum well where low band gap material is embedded between two large, you can say the same one material of large band gap on both the side. And this material act as the barrier or confinement layer, and this act as a well layer. So we can use the multiple quantum wells with the same material. So same material with the low band gap, same material, another material with a high band gap as a barrier layer. So they allow the larger volume of active region. So in each well, we can confine the charge carriers and can contribute to the photon emissions. So this is a basically structure of light emitting diode if we want to make, where we are making this is the either heterostructure, or you can make the quantum wells with the active regions and then the barrier layers and then current spreading layer. Current spreading layer is basically to ensure the injected current, if we are applying the forward bias, then the charge carrier should be uniformly distributed over the active region in this case. And the confinement layer, just as I mentioned you, is basically large band gap materials which confine the charge carrier from the active region. As far as active region is concerned, this is the small band gap materials which act as the well, where charge carriers are confined and can act as a collection of the charge carrier. So how the quantum well LED works? Basically, when charge carriers are confined, it's very easy to recombine the electron hole pair, and emission of photons are very easy. And when multiple quantum wells are there, then in these multiple quantum wells, the charge carriers are trapped in all the quantum wells, and all the quantum wells can participate in the emission of the photons, and that can enhance, you can say, the more and more photon emissions from the LED. So multiple quantum wells is the advantageous structure as far as LED is concerned. So basically we need multiple quantum wells of the materials, and on both the sides, one N-type material, one P-type material, and we can make a PIN structure like this. Now it depends upon us, depending upon the ease of the equipment, whether N-type material is at the bottom side or P-type material is on the bottom side. So structure can be anything, but the structure is that your quantum well should be embedded between the N-type and P-type semiconductor materials. And for that purpose, this is a proposed structure which we have planned to make the light emitting diodes, in which case this is the N-type semiconductor, and N-type semiconductor we have made by using gallium nitride doped with silicon. So we have tuned the conductivity of gallium nitride and make it N-type by doping the silicon. We can make the same gallium nitride P-type material by doping with the Mg. And in between, this is a quantum well of InGaN and GaN, Indian doped GaN and GaN. Indian doped GaN has lower band gap as compared to the GaN. So InGaN act as the well, and gallium nitride act as the confinement layer. And then we use a barrier layer just to avoid the leakage of this confinement charge carrier outside the quantum well. And these are the crucial parameters in the laser MB technique, which one has to play to grow the film. So what is the laser energy? What is the TS distance? How much RF power cells? How much is the pressure? So these all parameters has to be optimized, and you have to play with these parameters to get a very good quality gallium nitride thin film. So I will just glance quickly how this material has been grown by using the same laser MB technique, where we started with the gallium nitride on sapphire crystalline single crystal material, where the lattice mismatch is around 13 to 14%. And you can see by using the reflection high energy electron diffraction, this tool, we try to see how crystallinity improves in situ in the systems while doing the thermal treatment, while doing the nitridations, and while growing the gallium nitride. So this gives the advantage that we can see how material is growing. And you can see this is a SEM photograph and atomic force microscope analysis, where you can see with increase in the nitration temperature, the roughness is going to increase enormously. So we have to restrict ourselves up to the 700-degree temperature. So at this temperature, you can see your RMS roughness is almost same. So it's up to us whether we can go here or here, but the crystalline quality of the material is found to be good at around 700 with increase in the nitrate temperature. So we stopped here and we maintain this temperature. Now, as I mentioned you, the lattice mismatch is very crucial. So how this nucleation layer is concerned, so you can use the nanostructure nucleation layer, the zinc oxide, let's for example, nanorods are there. And on these nanorods, you can grow the gallium nitride, or you can use the silicon different crystallinity, you can use the sapphire. So different substrate one can try, and one can identify which one is good. But what we identified again, where lattice mismatch is less, we got the very good quality gallium nitride, single crystalline like the film, by using the laser MB technique, or any other technique also you can use with the same phases. This is some just idea I'm giving you how the material is growing by using this on silicon. So this is just graph on the silicon, where the films are not so good. They are polycrystalline. So all these materials are polycrystalline. So we restricted ourselves to basically sapphire substrate only. I don't know what happened. Okay, so I'm going with the sapphire substrate, gallium nitride. For that purpose, again, as I mentioned, there are several parameters. So we have to optimize the substrate temperature. We have to optimize nitrogen flow. And you can see here, as a function of time, how with 0.5 hours, 2 hours, 1 hour, this material is growing. And spotty structure is observed, which clearly shows that this material is very good quality material, and the termination here is N-type termination is there instead of the gallium nitride, gallium termination. And N-type termination is better for LED structure. Now, as I mentioned that I want to also use N-type layer. So to make the N-type layer, we have to dupe with the silicon. So with silicon duped, we try to optimize again the same parameter, and we have made N-type material with silicon doping. With Mg doping, we have to make the P-type material, but unfortunately, when we started, we are not succeeded with the P-type material. We got the N-type material. Then we increase the laser fluence, we increase the substrate temperature, and again we optimize, and then we succeeded in getting the P-type material. And then, if you can see here, under these conditions, there is no Mg traces are there. So incorporation of Mg was not there in the gallium nitride. So you can see the doping is not so easy. So for proper doping, you also have to give the growth kinetics, preferable growth kinetics. And now you can see here, Mg contents are present under the higher influence of laser and the substrate temperature at higher 800 degrees Celsius. Then Mg incorporation is there. Now we want to make the quantum well. So to make the quantum well, Indian incorporation we want. And we again optimize the conditions for InGaN also as active quantum well layer. So this is used as the well structure. So this is a charge confinement layer. So we change the gas flow, we change the substrate temperature, and we have tuned the band gap of this material. And now we try to fabricate InGaN quantum well for light emitting diodes. I can skip this part. This is more technical, where we try to find out the offset with InGaN and GaN. And you can see the offset here in conduction band is 0.22 and 0.19, which is more than enough for confinement of charge carrier in the well. And these are the barrier layers with gallium nitride. So we have made the quantum well structures of gallium nitride with InGaN. With any photonic devices, it's very important that charge collection is proper. And to make the charge correction, the contacts are very crucial. So we try different metals with this gallium nitride or indium GaN, N-type or P-type material. And what we found with after trying a lot of combinations, single layer, bilayer, multi-layer, aluminum gives after RTA, gives us the ohmic contact with the N-type materials, whereas ITO gives us the ohmic contact with the P-type materials. So this we identified after that. So these are the some analysis, whether the contacts are ohmic or not. So for that purpose, we have done the TL analysis. And by TLM analysis, we confirmed that these metals, aluminum and ITO, are found to be ohmic in nature. So we use aluminum and ITO as the electrode. And we started with simple PN junctions without quantum well first. So P-type layer, N-type layer, and in between intrinsic gallium nitride. And you can see with varying the gas flow, initially we found the rectifying behavior here. which is good for PN junction applications. And in electroluminescence spectra, we got the emissions in the UV light. Similarly, we try to make the PN junction with the other structure, inverted structure, where P type is at the bottom side. In the previous one, P side, on the bottom side, we use the N-type layer. So in this case, this is P-type layer. And again, we are getting the emission in the ultraviolet light. No defect peaks are there, which clearly indicates that laser MBE is very good technique to grow a very perfect interface gallium nitride InGaN structure, in the structure. So the same technique is extended to make the quantum wells of InGaN and GaN. And these are the two structures. In one case, we use the P layer as the bottom side. In another case, we use the N layer, N-type layer at the bottom side, and structure is almost same. One is inverted, one is direct. And we try to make both the structures of light emitting diode by laser MBE. And you can see here under one processing condition, this is device A, with increase in injection currents, how the emission of light is there from the light emitting diode. And we have not put any phosphor, we have not used any lens at the moment. It's a raw light emitting diode. And with second processing conditions, much improvement is there in the emission. And this is the photograph of the light emitting glow. And you can see here how this LED works. It glows and gives the light emissions here, and IV characteristics of light emitting, which comes out from the system. This is the inverted structure, and similar characteristics is obtained with the inverted structure. And here, chromatic analysis, you can see, here you can see that this cross point, that whatever emissions are coming out is in the low short wavelength region, which we are aiming, and blue LED or ultraviolet light LEDs we can develop by using laser MB technique. So we try to change also the number of quantum wells, the periodicity. So number of quantum wells, we vary from 3 quantum wells, 4 quantum wells, 5 quantum wells, 6 quantum wells, and 7 quantum wells. And by using the same technique, we try to find out the crystallinity. And then by using some sophisticated tools, we identify that 5 quantum wells gives the best response among all. And here you can also see that the 5 quantum wells are giving the best response. Conductivity, the carrier concentration is more, Hall mobility is more, resistivity is minimal. So we confine to the 5 quantum well to make the light emitting diode. So this is the basic characteristics, and we try to vary the quantum well structures. And then with 5 quantum wells, we have developed this light emitting diodes as an output, which just I showed you the curves in the previous slides. So all these are with 5 quantum wells structures. So 4, 5, and 6, but you can see the 5 quantum well is giving the electroluminescence much, much better, and emission is found to be much, much better as compared to other structures. Just I will spend just 2-3 minutes on UV photo detection by using gallium nitride. I can skip this part. I will go directly to the photo detector, where you can see when there is no light, it's a dark current. And when UV light falls, this current starts increasing because of photo generation of charge carrier. And when light goes off, it can come back. So this is a UV photo detector. And the time taken in this one is known as rise time. And in recovery, this is known as the fall time. The structure can be you can use the PN junction structure, and you can put the electrodes, and this PN junction can be exploited as photodiode, or you can make a simple layer, and you can make 2 contacts on top of that, and you can make either Schottky or ohmic contacts, and you can make photoconductor by using the photoconducting layer. So both structures are possible. So we tried first with the photoconductor structure, where we deposit the metals with Schottky, ohmic. So this is Schottky and ohmic contact. This is Schottky and Schottky contacts. And for that purpose, we again try electrodes, and we found aluminum is giving the ohmic contact. Palladium is giving the Schottky contact with the gallium nitride. Gold is giving the rectifying Schottky contacts. So we make the structures with ohmic aluminum and Schottky palladium. In this case, both are Schottky but asymmetric, palladium and gold. And these are symmetric one, where palladium and golds are there. And you can see we got the good response in the case of symmetric Schottky diodes as compared to the asymmetric Schottky diode as well as ohmic Schottky diode photo response. But the quantum well structures which we use for LED, the same structure we exploited for PN for this ultraviolet photo detection also. And in this case also we found that 5 quantum wells are giving the 4 times response from dark current to the photocurrent. So the response rise time, recovery time is very, very good as far as 5 quantum wells are concerned. The photodetectivity and photoresponsivity is very good in this case, and we are getting the response. In this case, is very, very fast. You can see 0.42 seconds or 0.48 milliseconds. Very fast response, which we got in the case of quantum well structures. We try to change the effect of lambda. We vary the lambda also, different lambda we put, and different bias we applied. And these are the optimizations with various bias and various lambda. So these are the ongoing research which is continuously going on in ultraviolet photodetector by using the gallium nitrides. So thanks from my side. I think I've taken enough time. Thanks a lot.
Thank you, sir. Thank you so much, sir. Thanks a lot, sir, for your this interesting and knowledgeable talk. I also again congratulate you, sir, for the Stanford ranking. It's a great pleasure, sir, actually for us, because you have accepted our invitation. Sir, we have a number of questions on the present.
No problem.
On this talk, study on gallium nitride and indium gallium nitride heterostructures and quantum wells by laser molecular beam epitaxy technique for short wavelength photonic devices. One is, sir, basically from Yogesh Kumar. He's asking, laser MB technique is used for short wavelength only, or it is used for long range wavelength also?
It can be used for any application, even for visible or even IR. It depends upon the material which you are using for growing. The band gap of material should be in that spectral range, and any material can be grown by using the laser MB technique.
Sir, one question actually from my side, although you have already discussed about the basically band gap tuning through the gas flow. Sir, actually I'm working on the perovskite solar cell heterojunctions, but only through the simulation technique, but want to work on experiments. So, sir, I have a query. How we can tune the band gap of absorbing layer in the multi-layer structures in the lab at the time of deposition, apart from this gas flow, sir?
Yeah, you can tune the band gap. One is by changing the thickness of the material.
Okay.
Lower the thickness, your band gap will be more and more. That's the one concept which you can do very easily. And secondly, depending upon the introduction of defect in the material, if defects are going to introduce, your band gap tuning is possible. And even if more and more conductivity is there, your band gap is going to reduce. And sometimes when conductivity becomes very large, even then the band gap increases enormously because of large collection of the charge carrier. So both possibilities are there. So a lot of possibilities as far as band gap tuning is concerned. One best technique is you can use the extrinsic defects or intrinsic defects for tuning the band gap. And secondly, if you don't want to introduce the defects in the material, you can use the interfacial layer. That means interfacial strain or stress is there that can also tune the material. Or if you have a single layer, you don't want the interface to exploit. In that case, the thickness is playing a very crucial role. So all these parameters you can use to tune the band gap.
Okay, sir. And the rest of the things I will discuss, and I will come to the lab and will discuss with you personally, sir.
No problem.
And one question, sir, is we are getting the perfect, it's question from Vish Acharya. Sir, we are getting the perfect characteristic for the cube LED, but we are not getting light. What may be the possible reason?
IV characteristics can be obtained by using your diode characteristics. It's not a problem. The problem is your emission of photons should be there. So either the emission of photon is possible only if radiative combinations are going to be there and should be in the excess as compared to non-radiative recombinations. So if non-radiative recombinations are going to dominate, your IV characteristics will remain the same, but it's very difficult to get the light out of it. So somehow you have to reduce the defects which are going to contribute to the non-radiative recombination.
Thank you, sir. I think there is no question. Ma'am, Vinita ma'am, can continue.
Any more questions? So you can write in the chat box.
No, ma'am.
Right. Or they can send me email, no problem.
Yes.
Yes, we'll share your mail, sir, and they must be having it.
Okay.
All of them. Thank you so much, sir, for the magnificent presentation and expanding our knowledge on the topic of quantum wells and heterostructures for photonic devices. And sir, for accepting our invitation to be the keynote speaker. We are really thankful to you, sir.
So I'm thankful to you.
Thank you, sir.
Thank
I
you.
would
Thank you so
also
much.
like to thank Professor P.K. Burma, Honorable Chairman of the College Governing Body, for his enigmatic presence in the inaugural of the session of the two-day national seminar. And we are really inspired by your words of great words and words of wisdom, sir. I would also like to thank Professor P.L. Unial, Treasurer, College Governing Body, for taking out time for us to be in the inaugural of the two-day national seminar and grace the occasion and delivering the words of wisdom. I would also like to thank the principal of the college for his positive guidance always and constantly motivating us to do better. Finally, I thank all the participants for being a part of the two-day national seminar. Thank you, everyone. Manish,
Yes, yes, ma'am. Thank you.
you
ma'am.
can
Yes, yes.
tell
ma'am.
them about the session.
Yes, yes. Now the session is for the invited talks. There is a minor correction. Actually, Dr. UP Singh was busy, or he will give his lecture on 12 to 12:30. And Dr. Subhash Sharma is from Mexico, and I forgot that there is a time gap of 12 hours, and there is a night. So he requested me to do his lecture before some 1 or 2 hours. So I have put his lecture first, and I think he has joined. Dr. Amit, please make the co-host. Dr. Subhash Sharma. Amit?
Yeah, hello.
Yeah. Dr. Subhash Sharma is here. Welcome,
Yeah,
sir. Dr. Subhash
thank you.
Sharma, yeah. I
Yeah,
want
I
to,
think, yeah.
I want to give a brief introduction about the Dr. Sharma. So Dr. Sharma is a PhD and MTech in physics and material science with 9 years of research experience in multifunctional materials. He has worked at Physics Department, Institute of Science, Banaras Hindu University as postdoctoral fellow immediately after his PhD. He has also worked with other international laboratories on materials for energy and environmental applications. He has over 35 research publications of international journals of repute, with H index of 11 and I-10 index of 12. He also rewarded one of the prestigious fellowship in the Mexico UNM DGAPA in 2017. It's a UNAM is in top 100 universities in international ranking. In the same year, he also awarded the one of the prestigious fellowship in the Chile. He also served as reviewer for AIP, American Institute of Physics, Springer, Wiley, and elsewhere for research. He also worked with Professor Rajiv Ranjan during his PhD in the year of 2012 in Indian Institute of Science, Bangalore. He is actively involved in various scientific projects and coordinating many activities of national interest at UNAM CNYN Mexico. Dr. Sharma is serving as an expert member of CONITE in evaluation of scientific projects. He is currently involved in more than 4 R&D projects. Presently, he is serving as a scientist at Trust position in UNAM, Mexico. His research area focuses on multiferric nanomaterials for green energy, multifunctional nanostructure materials, heterostructure via RF sputtering for energy and memory devices, and perovskite materials for photovoltaic applications. Sir, I welcome you in this scientific meeting and request you for your talk on the topic, the search for a practical multiferric material, the BFO-BST case, BFO bismuth ferrite and strontium dope barium titanate case.
Okay, okay, thank you, sir. I think,
Can you share?
I think I need to share my screen, but
Yes.
I think there is a request from your side or something. Like
Now, sir, now you can share your
Now you
screen.
can share, sir.
Your
Okay, okay. But actually, I'm not getting the.
Now you are co-host, I think.
Sir, you are the co-host. Please try it.
I don't know, but when I click on the screen, it doesn't show anything.
Can you email me your PPTs?
Okay, yeah. But can you check from your side? Maybe.
Sir,
Amit,
there is a icon, share screen. Click there, sir.
Yeah. I know, and
Blue one.
I'm clicking on that.
Uh, but not
But
getting.
when I click, there is nothing. Usually, when we click, it show your
Yes,
screen. But
screen. Okay.
yeah, but this time I don't know. Just a minute. Give me 5 minutes. I am sending to Dr. Manish.
Yeah, please.
But in the meantime, I am checking.
sir, have you selected this?
Yeah. Now it's coming.
Okay, sir.
Yes.
Okay,
Yes,
thank
sir.
you.
Now
Sir,
it's
it's
visible.
there.
Yes.
Yeah. Okay, thank you.
Sir, it's
So
visible.
first of all, I would like to Manish and sorry.
You can start, sir.
Hello. Can you hear me?
Yeah. Please, you
Yes,
can
sir.
start.
Yes,
Yeah.
sir. Yes.
First of all, okay, great. First of all, I would like to thank Dr. Manish and Dr. Arvind and other organizing committee and principal of this college to provide this facility to present my work at this platform. Actually, we are working on multi-frag heterostructure by RF splitting for memory application and for sensors. But today, I would like to talk about the BFO BST case. So in this talk, I will start with some introduction. What is multiferroic? What is magnetoelectric coupling? Some background of multiferroic and applications and motivation of the work. And finally, we are going to BFO BST case. So first of all, I would like to introduce means what is ferroelectricity? Ferroelectricity or we can say a ferroelectric crystal exhibit an electric dipole moment or means a crystal which can show the spontaneous polarization and that polarization can be switched by electric field is called ferroelectricity. And the requirement of ferroelectricity is the, as I said, spontaneous electric dipole moment and the last d orbital have no electron. And this polarization we can change with pressure, then it is called piezoelectric ceramic, and if we tune with temperature or change with temperature, then it is ferroelectric. And if we change this polarization by electric field or switching, then it is ferroelectric ceramic. In the same way, we can define ferromagnetism means a crystal which have spontaneous magnetic moment and that can be switched by magnetic field. And this magnetization can be changed by temperature and also changed by magnetic field. So in this figure, we have a mixed perovskite. In this figure, if you saw the green circle and the green arrow, which shows the ferroelectrically active D0 ions, and in combination of magnetic moment with the red one. And finally, what is multiferroics? Multiferroics are the materials which have which can so exhibit more than one primary ferroic order. Ferroic order may be ferroelectric, ferromagnetic, or ferroelastic. But the most important thing is that can be present in single phase. And in this figure, we can realize the coupling between the among many ferroic orders. Means how can we generate from stress to magnetism called piezomagnetism, and how can we induce polarization by strain or stress, and how can we change the electric field by means magnetoelectricity means change in polarization by magnetic field, vice versa. And if we look on these pictures, broadly speaking, broadly classified, there are two types of materials. One is magnetically polarizable and one is electrically polarizable, out of which we have some ferromagnetic in case of magnetically polarizable, and we have few ferroelectric out of electrically polarizable. And if we see, there are very few multiferroics, and out of these multiferroics there are very few magnetoelectric materials. So for device applications, the most important thing is the material should have high, means the material should exhibit high magnetoelectric effect. So this is magnetoelectric effect. Direct magnetoelectric effect means change in polarization by magnetic field and vice versa. So that effect is very important. So if we look some background of multiferroics, means started from 1888. Ronson, he stated that a moving charge can be magnetized when be placed in electric field. Followed by in 1894, P. Query, he defined crystal could be ferroelectric or ferromagnetic simultaneously in a single phase or multi-phase. In 1926, P. First defined he magnetoelectric effect, and following this, 1959, first they defined magnetoelectric effect in chromium oxide, Cr2 chromium oxide, and in 1960, Astrov discovered magnetoelectric effect first experimentally in this material. And finally, in 1994, H. Smith, he gave the proper definition for multiferroic, means a material which can show more than one ferroic order is called multiferroic. So the question is why we have so multiferroics? The condition for ferroelectricity and ferromagnetism is something contradiction, means for ferroelectricity we need material which is typically insulator, but on the other hand for ferromagnetism we need material means most of the magnetic materials are conducting. And of course for ferroelectricity we need non-centrosymmetry between cation and anions, but in case of magnetic there is no need. So almost all the materials in magnetic centrosymmetric between cation and anions. Typically we have transition metal which have vacant d orbital for ferroelectricity and partially filled d orbital for ferromagnetism. So that's the reason that in nature we have very few multiferroic, especially single phased material. So now we have many types of multiferroic materials, like single phase multiferroic, as I said, means if your ferroelectric and ferromagnetic order coexist in a single phase is called single phase. A composite material means we have taken one ferromagnetic and one ferroelectric and make a composite. So in single phase material we have type 1, type 2. In type 1 we have BFO, lone pair, charge ordering this material, and geometrical means when we have multiferroic due to geometrical distortions, this material. In type 2 we have spiral magnets and collinear magnets. But the focus of my research and my talk is only BFO. The question is why BFO? The reason is means we have these multiferroic materials, but if we can look, their TC means transition temperature from ferroelectric to paraelectric. TN means from antiferromagnetic to paramagnetic. So all the TC and TN are just either one is below room temperature or vice versa. But only BFO, it shows the ferroelectric and antiferromagnetic ordering well above the room temperatures. So it means we can use it for the device applications. But still in BFO, there are many problems. We will discuss in further slides. It has distorted rhomboidal structure, and in means one plane the spins are down, and in parallel other is the means adjacent plane is just opposite, means we have antiferromagnetic G type, and ferroelectricity just due to this lone pair of bismuth. And the most important, this length means spiral spin structure of BFO means some spins are this, and it means the shape of spins are going to be not suddenly change, but in a period of 62 nanometer. There are many applications of multiferroic materials, means we can use in tunable microwave devices, tunnel magnetoresistance, multiple state memory devices, spintronics, spin valve, and photocatalyst and optoelectronic devices. The main challenges with BFO, the first is the synthesis, means it's not easy to synthesize single phase, and the high leakage current due to existence of variable oxidation state of iron, and for charge compensation or bismuth or means loss of bismuth during sintering. There is some oxygen vacancies, and also although the in bulk form BFO is antiferromagnetic, but when you make it by sol gel in nano form, it is showing weak ferromagnetism, and also it shows weak magnetoelectric coupling, weak ferroelectric nature in bulk form. So to overcome these challenges, we have carried out some literature survey, and these are the findings and findings of these research papers. So till now we have no good single phase multi-frag materials. So we are planning to do with some ABO3 type structures. So we have decided to do with BST, the inner fixed composition barium and strontium. And in this we have synthesized these samples or this set of samples with simple sol gel assisted route, and we characterized structural, electrical, magnetic and ferroelectric properties. So let's see what we have done and what we have got. So we carried out structural characterization by XRD, and if we see the main characteristics plane for the R3 rhomboidal structures, the plane 104 and 111, and ABC in the large view. So from 0 to 15, the main characteristics peak of BFO is not going to change in single peak, just rather it shows some broadening or shifting. So for 20% we have a perfect, not perfect, but broadened one single peak. So one single peak. That means we have some structural phase transition from 15 to 20. So in order to confirm these structural phase transitions, we have carried out Ritwell method for these compositions. And based upon the fitting parameters, we have concluded that up to 15% there is a rhomboidal structure, and from 15 to 20 there is a structural phase transition from rhombohedral to tetragonal. And these are atomic positions, bond length and bond angles. After that, in order to confirm these structural phase transitions, we carried out Raman spectroscopy for these samples, and we have seen that almost same shape of the Raman from Raman band from 100 to 600 for 15%, or maybe that disappearance of some Raman modes starts at 15. It means the signature of phase transition starts. So maybe it may be because we have only 15 and 20, but maybe for it 0.16, 0.17, maybe already they have structure changed. But for 20% we got the this Raman spectra. So from this results means when we dope BST in BFO, so around 15% it starts the change in intensity of some Raman modes and disappearance of some Raman modes. So it means it suggests there is some structural phase transition for these compositions. So overall means this Raman spectroscopy supports our Ritwell results. These are observed Raman modes and we compared with the literature, and we have found good agreement. After that, we have carried out dielectric measurement, and from room temperature to 500. And if we see, we have a small two kink at one at 270 and one at 345, only for this 1 kilohertz. This 345 kink may be due to the magnetoelectric coupling, because at the same temperature around 350 we have a nil temperature. So means when we apply, means we are measuring dielectric properties, but we have some variation around nil temperatures. So it shows the direct indication of magnetoelectric coupling in these samples. And for 5% we have this, but for 10 and 15%, this kink shifted to high temperature 335 or 345, and this this king attributed to some defects in BFO. But and if we talk about the loss, so at room temperature at 100 kilohertz, the loss is less than 1, and I think is good. In order to confirm the leakage current behavior for these samples, we have carried out leakage current measurement, and we found there is significantly decrease in leakage current when we doped with BST. So it means just due to because the strength of barium oxygen bond is higher than bismuth oxygen. So it means that when we dope the barium, it restricts the evaporation of bismuth. So means there is no oxygen or no electron. So means there is no evaporation of bismuth from the sample. So we have perfect reduction of leakage current. And it can be the requirement of charge compensation, because when we do higher balance on the Fe state, because titanium is 4 positive and Fe in iron is mostly in 3 positive, but it can be 2 positive. So these are the conductivity behavior, and we fitted with Arrhenius equation, and we divided the whole is in 3 categories. This is low temperature, intermediate, and high temperature. So after fitting, we have calculated the activation energies, and on the basis of these activation energies, we can propose a suitable conduction mechanism. And these are the dielectric properties. If means overall, if we see the dielectric constant is going to increase and dielectric loss overall is going to decrease. However, for 15% it again increases from 20 to 31. So the activation, and we have calculated the activation energy for a different reason. In the first reason, the activation energy is from 0.05 to 0.13 electron volt and is attributed to local hopping of electrons. In the second reason, based on the activation energy, it may be due to the role of oxygen vacancies, and same for the third reason, maybe single or doubly ionized oxygen vacancies. After that, we have carried out magnetic behavior to check whether from pure BFO is going to enhance or going to be reduced. So as we know, BFO in bulk case is perfect antiferromagnetic, but these samples in the nano resins, so they are showing some weak ferromagnetic behavior due to if we remember, we have a perfect 62 nanometer range of antiferromagnetic coupling. If we disturb that 62 nanometer length, so maybe there is a release of some locked magnetization. So maybe the reason for this 0%. But again, when we do it with BST, so maybe it changed the structural distortions and changed that 62 nanometer length, and we have a good increment in remnant magnetization. However, for 15 and 20%, the overall area of magnetic means magnetization is reduced. But when we talk about remnant magnetization, it's going to be increased linearly. So the reason is, as I said, means the partial destruction of spiral spin structure and also structural distortion caused by BST doping. After that, we have carried out ferroelectric behavior, and for BFO, the remnant polarization is around 2 point something, it's 2.05. But when we doped, means when BST goes into the BFO lattice, the structural distortion and the stereochemical activity of A site means bismuth is going to be changed. So that change may be contribute to the polarization. And also, as we seen in the dielectric properties, means there is a restriction of bismuth evaporation. So we have a more stable dipole moment in terms of barium and oxygen. So conclusion from XRD and from reticular refinement, we have concluded that up from 0 to 15% it is just distorted rhomboidal structure and changing lattice parameter. But from 15 to 20, there is a structural phase change from rhomboidal to tetragonal. And as concerned dielectric properties, so overall the dielectric response were improved as we do with BST. And also we have seen the decrease in conductivity just because of maybe suppression of defects in these samples. And we got the significant increment in magnetization from point means for 20% we have 0.488, and for 0% we have something like that from 0.06 AMU per gram. And also we got increment in polarization for 20% from 2.0 means around 2, and for 20% we have 10.11. And also we have seen the significant decrease in leakage current for these samples. So the conclusion of this talk is still we are searching for the single phase material, but yet we have not achieved the good multi-phase properties in single phase. But if we dope the material with some means make some composite, so maybe we can tune the, or we can achieve the good multi-phase and magnetoelectric coupling. So maybe I was too fast, I think. So I think thanks from my side. And presently we are working multi-phase heterostructure, spintronics, experimental DFT view, some perovskite for photovoltaic applications. And also we are offering some PhD and postdoctoral positions. So if any questions you can ask.
Yes, sir. So there are some questions. First of all, thank you for your nice talk. And
thank you, man.
There are 2-3 questions.
Okay.
First from Dr. Sankar from our college. I hope you know he's.
Yeah. I know him very well.
As per Sankar, very nice talk. How to differentiate the solid solution and composite systems using Raman spectroscopy.
Okay. Yeah. Suppose if we have a composite, it means we have a means if we see in XRD or maybe in Raman, suppose we have BFO and BST. So in Raman spectra we have mode, means we observe mode from BFO as well as some Raman mode from BST samples. Same in XRD. Means we have maybe perfect rhombohedral for BFO and BST for tetragonal. So in XRD we have some peaks from tetragonal, some peaks from rhombohedral. But if we have a solid solution means the barium and strontium try to go at bismuth site because it's a solid solution. It's not a composite. Means in one hand we make BFO and then we make BST, then we mixed. That is composite. But in this case, we means before calcination we just take an appropriate amount of barium, strontium and bismuth and make solid solution. So I think if it is solid solution, overall it shows the BFO means host BFO properties. But if it is composite, so means somehow BST is going to be dominant, I believe.
Thank you. Sir, one more question from our one other colleague. Right now, I think he is in Brazil, Dr. Mahesh Chand. Excellent talk, Dr. Sharma. Anyway, I need one clarification. As you obtain XRD and Raman studies, can you correlate these two measurements?
Mm-hmm.
This is a question.
Okay, yeah. If you see in XRD, as I talk, I think maybe if we can see from 0 to 15%, there is the same structure, and in Raman spectra, up to 10%, it's almost means same number of Raman modes. But when we go to 15%, although in XRD, in 15% it shows rhombohedral, but maybe from 15% it starts to going to other crystal structure. So as I said, because we have not 0.16, 0.17, so maybe at 0.16 already phase transition occurred. But in this case, we have from 15 to 20. So from 15 to 20, there is drastically means if we saw the main or maybe characteristic summary mode of this around 180. So we have for 0, 5, 10, 15. But if we speak about 20, there is, for me, I think no. There is no mode around 180. So I think in this way we can correlate this structure.
Yeah. Okay. Okay, sir. One question actually I want to ask, sir,
Yeah,
is
please.
there any practical application through any multi-ferric material, either bismuth ferrite or any, that is present in the society till now? Or what is the possibility?
Yeah, as I said, means all the researchers are trying to find the good multiferric and having strong magnetoelectric effect. But unfortunately, in single phase, we have means no one achieved the good magnetoelectric properties. So I think in industrial scale, still there is no use of this. But maybe for just means
Yeah,
means I
maybe.
mean to say, yeah, on industrial scale there is nothing, I think.
Okay, sir. Okay, thanks a lot, Dr. Arvind. Dr. Arvind?
Yes,
Yeah,
yes.
yeah.
If there is no more question, then I once again would like to thank you, Dr. Sharma, for accepting our invitation between his
Okay, thank you,
busy
sir.
schedule,
Also, I would like to thank to you.
and especially lag in time in between two different countries. And
Yeah. Also, yeah, sir, just a minute. Also, I want to share that maybe in future we can plan some India-Mexico international conference. Maybe we can organize
Yeah,
sure,
this.
sir.
sure.
Yeah.
Sure,
Sir.
sir.
Okay.
We are also thankful to you for such a nice and brief talk on multiferric materials, which are the key materials for the present day technology. And surely, if we achieved a good multiferric materials, we can apply for technological applications
Yeah, sure.
soon in the future. So
Okay.
once again, I would like to thank you. Thank you, sir.
Thank you, sir.
Thanks, sir.
Thank you so much.
Thanks. Our next speaker is Dr. Dr. Ravi, Dr. Santosh Kumar Ravi, Dr. Sai Santosh Kumar Ravi. Amit sir, please make the post.
Good morning. Good morning.
Yeah, good morning, sir. Good morning.
Good morning, sir.
I want to give some brief introduction about sir. Dr. Ravi is currently working as Associate Professor at Indian Institute of Technology, Hyderabad, and his area of research interest is on optical time-resolved spectroscopy and ultra-fast nonlinear optics. He was a visiting fellow of electrical engineering, Princeton University, USA, and visited many countries at the different research positions. He is the recipient of number of awards, such as joined the editorial board of Energy Materials as review editor for Frontiers in Materials, selected as OSA Senior Member of Class 2020 Optical Society of America, nominated as Associate Fellow of the Telangana Academy of Science for the year 2019, Bhaskar Award Solar Energy Fellowship 2018 funded by Indo-US Science and Technology Forum IUSSTF to visit Princeton University, USA during May-August 2019. FAPSP Visiting Research Fellow during June-July 2017 to visit Institute of Physics, University of Sao Paulo, Sao Carlos, Brazil. He has published more than 61 international publications of repute and one book chapter. Sir, I welcome you in this scientific meeting and request you for your talk on the topic rare earth doped photoanodes for organic molecule-based solar energy conversion devices. Sir.
Thank you. Thank you. Thank you for your introduction. It's glad to give a nice talk. I've been sitting and listening all the talks from the morning. It's a good meeting which you have organized, and I'm very privileged to give the talk here. Today's presentation is titled Rare Earth Doped Photoanode for Organic Materials Based Solar Energy Devices. Just a minute, sir. Let me just start my. Yeah. So there are few things which I should introduce you. So this is the plan which I'm going to do. I would just briefly tell you what are the various organic photovoltaic devices, just based on the solar energy conversion devices. I just named it as a solar energy conversion devices because there is more than one technology which uses this kind of photoanodes. And I briefly explain you in 1 or 2 slides what is TiO2 photoanode and what are the problems associated with this, and how we are going to use the doping to improve the performance. And I will present our latest results on neodymium doped TiO2, where we have done extensive study from both physics, photophysics, and device physics point of view to find a universal doping concentration and what is the physics behind the enhancement obtained with the devices based on this neodymium-based doped TiO2. So this is how I plan my talk. First thing is the motivation why we do this is for a photovoltaic technology to satisfy the. Hello, can you hear me?
तो तौलिया डालना फोन पे बैठने के बाद
Yes, sir, yes.
Yeah, for a photovoltaic technology to satisfy the sustainable criteria, it should be economical, made from earth-abundant resources, along with lowest environmental impact. The reason why this statement is very, very important is that no doubt we see a lot of growth in the photovoltaic industry. We do see a lot of advertisements where they say that you put on the solar panels to get green energy. But there is a problem with the silicon solar panels, which we see all around. And this silicon panel, the biggest problem is that the production of silicon or the production of the silicon wafers as well as the silicon solar cells from the most abundant silicon source, that is the sand, which we see silicon dioxide, is very expensive, high temperature intensive, and also the kind of chemicals they use to make the process to follow the various processes processing technology is highly harmful to the environment. So there is a lot of carbon footprint which is being generated because of the production or manufacturing of these silicon solar cells, and that's why researchers have moved out for finding out an alternative form of solar cells where the sustainable criteria is improved. So in this way, in this point of time, as well as this scenario, the organic solar cells are fitting the bill, and a lot of research has been going on in that direction. And as I mentioned just now, all that a silicon solar cell is not possible with silicon solar cells. Organic photovoltaics allows such things. For example, it allows the possibility of low-cost fabrication procedure. You can print this on flexible substrates. You can engineer the molecules to tune their band gaps so that you can adjust the solar spectrum the way it is, increase the absorption, and so on, and also the increase absorption as well as the charge transfer characteristic. And importantly, it offers a potentially less hostile environment, environmental behaving. So all these things are very, very important points why research have progressed towards development of the organic photovoltaics. As I mentioned, it's not just one technology. There are a number of technologies which form this overall area of organic photovoltaics. They are organic solar cells or polymer solar cells. You have the dye-sensitive solar cells and hybrid solar cells. Right now, hybrid solar cells is the talk of the town. It's very hot, where they talk about the perovskite solar cells and quantum solar cells. So everything is now being explored a lot. And if you see the NREL website, which updates the best efficiency or certified efficiencies every 6 months, you see that the field of organic photovoltaics started sometime around 1992, and every decade there is a new technology which comes and which does a disruptive kind of effect to this field of organic solar cells. If you take the first part, which is the 1992, the dye-sensitive solar cell was introduced, and within no time it reached the maximum of about 10.5 or 11.5%, and it continued to stabilize. It is in spite of a lot of research for next 20 years, and at the moment the best efficiency is about 12.3%. 10 years later, there is a new concept called bulk heterojunction solar cell with polymer-based donor and acceptor, small molecule fullerene-based acceptor, which started in University Lynch in 2003, around 2002-2003, where it started with about 2% efficiency, and it has now reached a world record efficiency of 17.4%. And again, 10 years later, okay, I would just skip these points. 10 years later, there is the most disruptive technology in organic photovoltaics, that is the advent of the perovskite solar cells, okay, where straight away the first efficiency reported was about 12% in 2013, and right now it is close to the 25.2%, and with tandem solar cells, like if this is a perovskite silicon tandem, you have the possibility of getting more than 30% at the moment. So now the numbers of 25, 30, they are close to what is being offered with the silicon and inorganic solar cells, and that's where the ability or possibility of seeing organic solar cells in market soon is more. Okay, so in the next 10 years, I'm sure there will be a lot of products which come out based on this organic photovoltaics. Of course, the various other technologies which are being pushed is also continued for very specific applications. We believe that in another 10 years, there will be a good possibility of finding this applications in day-to-day life, right? Now, important point about this organic photovoltaics is that these are slightly different to that of inorganic solar cells, and it is different because these are all classified as excitonic solar cells. So what is excitons? Okay, just to differentiate between the inorganic semiconductor and organic semiconductor. Inorganic semiconductor exhibits this kind of van Neumann excitons. It has van Neumann excitons where the exciton binding energy is almost comparable to that of the thermal energies. Okay, the point is inorganic semiconductors allows you to have a very crystalline material system, because of which the exciton can get delocalized. Or the point about what I mean to say is that if the electron hole pair forms in one area, in one location, the electrons can delocalize for longer distances till the binding energy supports, and that allows the possibility of dissociating it much easier. Okay, that's the point about this PN junction, where the inbuilt potential, which I say VBI, is sufficient to make the excitons generated in a silicon PN junction. Contrary to this, if you take the case of organic semiconductors, by virtue of these organic materials being highly disordered, they exhibit the so-called Frenkel exciton behavior, and the excitons are highly localized, because of which the binding energy is very high. And if you generate an exciton in an organic semiconductor, to dissociate this exciton into free charges, it takes some energy. And that energy is obtained by forming the so-called donor-acceptor interface. Okay, and that's the main reason why these are called the exciton solar cells. And the whole field of this organic photovoltaics is based on how good one can find a way to dissociate these excitons, right? So first, as I said, the first technology which was introduced into this OPV community is the DSSC, where you have the where this dye-sensitive solar cell, mainly a liquid-based dye-sensitive solar cell, is consisting of three components. One is a dye which does the job of absorbing the light from the sun. Okay, it absorbs the light, and this dye is sensitized as a monolayer over the mesoporous titania or any metal oxide, right? Titania is more famous, so I just put this word, but typically any metal oxide like metal oxide semiconductor like tin oxide, zinc oxide can be tried. And the point is what happens here is that you have the exciton, so the molecule gets excited because of the favorable energetic placement, where the LUMO of the dye, which is the lowest unoccupied molecular orbital of the dye, is chosen such that it is higher than that of the conduction band of the acceptor. You have this so-called electron injection. So now what happens is that this dye absorbs the light, gets excited, injects an electron to titania. Titania, being an inorganic semiconductor, exhibits faster electron transport. Okay, it exhibits faster electron transport, and this electron which is injected quickly moves towards the electrode which is here and goes through this circuit. Now this dye, which lost an electron, is now oxidized, and it looks for any source of electrons in the surrounding, which is obtained by the presence of the liquid electrolyte, which has excess of electrons. So there is a redox reaction which is possible here, where because of the redox reaction between the 3I- and I3-, there is a electron given to the dye. So basically what this particular process is called the dye regeneration, and the dye gets regenerated into it gets an electron. So so that way this oxidized dye becomes neutral again, ready for the next cycle of absorption and electron injection. Now then the electron which is being donated by this, or the hole which is given from the dye to the electrolyte, slowly moves or percolates through this counter electrode and it meets with the electron, and this is what we call as the charge recombination at the counter electron. So overall, all this process allows you to generate electricity from the light, and this particular technology, more or less, if you see, it is inspired from the way a plant does the photosynthesis, where different parts of the different molecules in the plant leaf does this kind of inject electron charge, light absorption, electron injection, energy transfer, etc. So this is similar to do that of that. So more or less, this has been explored a lot, and I would say this is most mature technology till now, and many of the commercial products have come. There are still issues with that in terms of usage of the liquid electrolyte, so we'll not get into that, but the point is that you do have very good efficiency with this. Next is the concept of silicon polymer solar cells, where you have a bicontinuous network of donor acceptor blend, where the polymer absorbs the light, forms the exciton. Then the excitons doesn't get dissociated because of the high binding energy. So it somehow percolates, diffuses to the interface, and then you have the exciton dissociation at the interface. Once the excitons are dissociated, they would nicely go through their respective pathways to form the eventual current. Right now, the point about this is there is certain limitations where you have the charge transport mechanism, limitations for this kind of photocurrent, which is in the OSC, and this comes in the point of into these two categories. You have the diffusion of exciton to interface, which forms the first limitation. If there is a trap, it doesn't get diffused. Second is the charge separation. So if this is possible, if you can come out these two steps, then the third step is the charge transport, where it tries to go towards the respective cathode and anode. Now the charge collection, where the charges have to leave the active material and go to the anode or the cathode, forms the next barrier, and that overall is the problem of the morphology of the entire system, of the morphology of the active material, as well as that of the energetic mismatch between the active layer and the anode or the cathode, which limits the performance of the organic solar cells. So to come over these limitations, the researchers have come up with this so-called interface engineering, where they found that by choosing a donor acceptor rich ends, they could improve the interface, they could improve the efficiency better, and the best efficiency was found by choosing the right interlayers. Okay, you have the electron separate, depending upon the choice of the interlayer, hole selective or electron selective, you have higher efficiency. And this interface engineering is found to be critical in improving it, because by choosing the right interlayers, you could tune the energy level alignment at the electrode. Okay, it could define the polarity of the electrodes, control the surface properties of and alternate the morphology. Also, it could allow the optical spacer, and you can introduce optical spacer and plasmonic effects because of this choice of the right electron selective layers. And importantly, the different layers were found to improve the interface stability. Okay, now if you look at the interface engineering issues, typically the titanium or the metal oxide were the best possible material system for electron selective layer, and that's where the metal oxides were employed routinely. Then comes the concept of hybrid solar cells, where the semiconducting polymer is used as a donor, and then instead of using the fullerene as an acceptor in the bulk heterogeneration concept, you just pick up this nanostructured metal oxide from the DSSC concept, and you try to put them together to give you the so-called hybrid solar cells, right? So the same thing happens. Polymer absorbs, injects the electron, and hole transports to it. Now this was what the genesis of the so-called present perovskite solar cells, because this particular arrangement was found to be bad for various reasons, and they replaced this semiconducting polymer with the perovskites, right? The perovskites now are the talk of the town, as I mentioned at the beginning, and organic heterogeneous perovskites have emerged recently as promising candidates for next generation photovoltaics and lighting applications, with the best efficiency is more than 25.5%. Again, if you try to look at all these things, they are the ones which give the light to current by absorption and exciton dissociations. The other option is the so-called photoelectrochemical water splitting, which is typically exploited to generate more hydrogen, because hydrogen was widely considered to be a clean fuel. Here, the metal oxide chosen as a photoanode does this kind of reaction where you have TiO2 plus what it absorbs the light and forms the exciton electron hole pair. Then these electrons interact with the water which is around. Okay, it's similar to the electrolysis which you talk about. Here we call it the photocatalysis. So here the water is interacting with the electrons to form oxygen and 4H plus, and 4H plus 4E might gives 4 hydrogen or 4H, and that's how you separate the water and oxygen separately between the two electrodes, and you can generate hydrogen. At the same time, all this process allows you to generate extra a photocurrent. Okay, depending upon the choice of this material, you have the photocurrent as well. So you have the possibility of solar light to hydrogen generation plus the formation of current in the circuit. So all these things were found to be a new concept here. I mean, people have a lot of work is being pushed in this direction of water splitting. Now, if you look at all these things, which is common, is the in all this organic photovoltaic devices, the most common material is the acceptor and electron transport layer, and that's where the main talk about this particular work comes into picture, which is the titania as a photoanode. As I mentioned, titania has been exploited a lot. In fact, it is not a new concept. Right from the beginning of 1992, which I just showed you in the first slide, in the earlier slides, they have used titania as a photoanode. This is because a favorable position of the conduction band, it's a wide band gap, relatively low fabrication cost, it has stable electrical resistance, series resistance states, high electron drift mobility. All these things contribute to the choice of titania as the correct or the most common photoanode in all these technologies. And as you see here, for everything almost everything what I mentioned in the earlier slides, you can find a role of titania or the photoelectrode, and titania seems to be the most used choice for the photoanode. Okay, now there are some limitations, and the main limitations comes into picture where the presence of high density of electron trap states lying below the conduction band. So the conduction band and valence band, and it was found that through both by DFT as well as experiments, there's a presence of high density of trap states, which sort of trap the electrons and doesn't allow the charge transport. Second point is it has large band gap, and therefore it allows only absorption of light of UV region. Importantly, for the case of the water splitting experiment, you can do only with respect to only by using the UV light. You cannot really convert this solar spectrum, which has less UV light compared to the visible and infrared, into the hydrogen fuel or the current. So overall, because of these two main limitations, it was found that one can do some changes in improving the absorption by dye-sensitization. Try to play with engineer the traps by doing doping, particle size modification as well as surface modification by various dopants. A lot of dopants were used, and among them, radar doping effect is what is the talk of this presentation. And it was found that radar doping, along with the improvement in the absorption, could also change the way the doping, change the way the traps can be engineered, right? So this is the main point about radar dope effect within titania. It induces surface trapping sites. It is reducing the charge recombination, and importantly, the intrinsic 4F orbital transitions within the radars is allowing you to have a reduced band gap. This is clear from this Jablonski diagram. So the first three parts are the what happens in the normal titania, and by introducing an anthenide or the rare ions, you introduce the optical excitation within the 4F transition, because of which the overall band gap of this doped titania reduces. Okay, so all these things are the main reasons why the rare doped titania were exploited. And here in this work, we present our results on the neodymium-based titania, how neodymium has improved. The choice of neodymium is because neodymium allows you to have absorption all the way till near infrared, and it has emission into the near infrared. And one can try to find a co-doping. Eventually, you can cover the entire visible to near spectrum by choosing the neodymium. So this is the reason why we went about trying to understand how the neodymium doped titania would behave. Okay, so what we do is we follow this protocol where you make the titanium doping, do the characterization, make the paste for making the photoanode, and then do the solar cells or any other devices. Okay, so in this, I would start with the physical characterization of ND-doped TiO2. The first point is the XRD. Once you make the material, XRD gives you the right way to know whether there is a proper substitution of this dopant into the lattice, because if it is not substituted properly, that would distort the entire lattice and titanium would not behave like titanium. If you see from this XRD patterns, you see that by small doping concentration of 0.2 to 0.5, the overall XRD pattern doesn't change, just that there is a small shift in the peak position towards the higher angle, and that is what introduced the so-called strain, because the large ionic size of radius of ND enters into the titanium lattice, and titanium has a smaller radius, because of which ND replacement leads to a change in the crystallinity that would have a small strain in the host compound. Why the strain is important is that with this strain, one can expect the formation of more oxygen vacancies, and that is what is eventually turned out to be the main reason for better performance in this doped titanium. Okay, then we did the WH plot for Williamson-Hall plot for the XRD pattern, and we calculated the size and strain, and you see that with increase in the dopant, the strain is slightly reduced, becomes little bit different. The size is reduced as well as the strain is reduced. Okay, and we concluded that neodymium has strong hybridization with oxides compared to titanium, so it restricts the titanium crystal growth. Small grains can decrease the disorderness in the compound, so the strain also gets decreased for activation of disorderness compared to higher grain size components. Okay, so all these things gives a indication that one can keep on doping till to reduce the size in the strain, and this would have a better effect. In fact, if you look at this data, you find that the size is minimal for 0.4, and that's where we started trying to find that 0.4 may be the right dopant for the improved performance. However, we did further studies, and the next thing is the UV visible spectroscopy data, where we tried to bring in the concept of reduced band gap. And if you look at the absorption of it, we find a characteristic absorption band of neodymium in this region. And the top plot shows that the band gap is reducing. If you see this from pure titanium to ND-doped titanium, the band gap is reducing from 3.25 to 3.19, suggesting that there is more formation of tail states. And the tail states are then characterized using this so-called Urbach energy analysis, where this particular equation gives you the how one can get the Urbach energy calculations. Alpha is the absorption coefficient, alpha naught is the constant, and it represents the structural disorder in the host materials due to low crystallinity, trapping states, surface defects, and electron-proton interaction. So overall, one can try to fit this tail states in order to see how is the Urbach energy coming into picture, which is the EU, right? So EU can be obtained from that value, from this fitting by using all these things, and it was found that the Urbach energy is increasing with increasing dopant. Okay, or in other words, it was found that the alpha naught, or the constant that represents structural disorder, is improving with Urbach energy with the dopant, and this gives an indication that there is a formation of new surface defects which might lead to the so-called higher oxygen vacancies that may lead to a further improvement in the charge transfer. Right, this is the main point about it. Then we did to actually look at the surface charge defects or the oxygen vacancies with the XPS study. This is the surface spectrum, which talks about how good is the doping taking place. In fact, if you do a more high resolution X spectra, we find that there is ND3 division, which is here. The binding energy is here, and this fits well with the reported literature. The most important point of the surface charge, so surface oxygen defects come into form by looking at this particular Ti2P orbital change. If you see, it is here we talk about the Ti4 plus orbital change, and for TiO2 and NdTiO2, the peak strength has gone up. Okay, this Ti4, this peak strength, the strengthening of the Ti4 plus peak gives an indication that there is formation of surface defects at the conduction band level, okay, or the oxygen, or the so-called the oxygen defects at the conduction level. And to understand how it affects the valence band or something which is deep lying states, we looked at the O1s spectrum, and we find that the doping of titanium with Nd reduces that particular band. Okay, so here it says that in this figure C, or the we say that there is an improvement in the increase in the surface states or surface defects, and here it says that there is a reduction in the deep lying oxygen defects. So the main message from this particular experiment is that if there is a charge which is injected into the titania or the conduction band of the titania, these surface states would allow faster transport. And because there is reduced deep lying states, the electrons which are injected into the titania would not get trapped into the deep traps of the titania, which could be present in titania. And by doing the dopant, we could reduce such traps. Okay. Then we started looking at the dielectric properties of this material. We find that the dielectric constant is increased with doping. Dielectric constant increasing, improvement in the dielectric constant result gives you information about better polarizability. And from the point of view of solar cells, we find that the resistance is reduced for 0.4 TiO2 and Nd 0.4 TiO2. And at the same time, the conductivity also increases. So overall, this is the Cole-Cole plot, which plots between the imaginary to real Z impedance. It gives an indication that the grains, the resistance at the grain is reduced for the 0.4 dopant. And overall, all these things, all the experiments, they give us an indication that the 0.4 TiO2 seems to be the right photoanode for the devices. And we went about making the devices. First thing is we made the sensitization of cadmium sulfide quantum dot as well as the dye-sensitized TiO2, and we find that the photoluminescence quenching of these photoanodes is stronger for 0.4 doped NdTiO2, and also the TRPL data, time resolved luminescence data, tells us the charge injection is much faster for the photoanodes with 0.4 Nd doped TiO2. So just for those guys who are new to this concept of photoluminescence quenching, it means to say that when you excite a material system like cadmium sulfide or titania, or the dye which is without the titania, you have the natural lifetime of the natural excitation and natural decay lifetime. And when there is a acceptor system, the charge is injected. Okay, so there is a quenching of the luminescence. Now, higher the quenching, higher is the charge injection probability, and we see that already with respect to I didn't show the actual data of CDS because that will be much higher. I just show you that CDS in titania is a known photoanode for quantum dot solar cells. You do have charge injection, but we see that this charge injection is further improved by doping of titania with neodymium of 4.4%. And the same thing one can see with respect to the dye. Just like how we see with the quantum dot, we see that even with the dye, we see the quenching is higher for the 0.4 Nd 0.4 TiO2. And both of them gives us an indication that Nd 0.4 TiO2 should give you a best device properties, and that is clear from the JV characteristics we found from the dye-sensitive solar cell as well as quantum dot sensitive solar cells. In this slide, I show you the dye-sensitive solar cells, and you find that the efficiency has improved from 5.5% to 6.4%. And because I've been harping all about increasing the charge transport, that would directly improve, that would directly manifest itself as improvement in the short circuit current. And you see there is an increase in the short circuit current compared to the titania dye to Nd4 0.4 titania dye. Okay, so 10.2 versus 11.8, and so the efficiency is increased. Similarly, for the case of cadmium sulfide, we see that there is a increase in the charge in the efficiency as well as the JSC 6.33 to 6.67, and here 1.4 to 1.82. And also we find that somehow the VOC is increasing for the case of Nd 0.4 with respect compared to the TiO2. So overall, this particular dopant found to have a constant optimization of the optimized dopant of TiO2, Nd on TiO2, found to give the best performance compared to the undoped ones. Okay, then we went about looking at the properties of the impedance, how the impedance is actually mattering. Whatever we studied in the earlier that is for the pure TiO2 or NdTiO2 without any solar cell device, where we talked about the dielectric property, real and imaginary impedance, etc. In devices, we wanted to look at how is the transport working out, and we find that the we do this kind of fitting with the circuit, and then we find that the various resistance which can be worked out or fitted based on the fitting of this EIS spectrum, where you get R1 to be equal to series resistance, R2 is the interface resistance, and R3 is the recombination at the counter electrode. We find that for the case of 0.4, the resistance, everything is reduced. So here you have the R1 and R2 should be less, series and interface resistance should be less compared to TiO2. Yes, this is how it is. In fact, it's very less for the ND 0.4 TiO2. Somehow the interface seems to be very good when you dope it. And for the R3, the recombination at the counter electrode should be high, because higher the recombination, higher is the electron hole pair recombinations, and that you can see to be very, very high for the case of ND 0.4. And we see the same thing for the case of TiO2 with CDS. Okay, in this we do see reduced number for R3, but R1 and R2 is also how much lesser compared to the TiO2. So overall, we find that the for both dye sensitized as well as quantum dot sensitized solar cells, doping of 0.4 NdTiO2 seems to be the best performing device. Just to finalize, just to complete the story, we also went about doing the solar spotter splitting experiment. I would like to credit Dr. Praveen Meduri of Chemical Engineering Department, because I'm not an expert in this particular field. However, we see that just for the completing the story, we see that the the current density for titania CDS and titania dye electrodes, photoanodes in the photosplitting solar cell water splitting device is much higher than that of the pure titania. This is for the 0.4. Okay, this is the 0.4, and compared to that with the black, which is somewhere here. Okay, so there is an increase in the current density which is coming out, and efficiency of solar to hydrogen generation, it seems to be improved for the right dopant. In fact, it turns out to be 1.2% at 0.3 for ND 0.4 TiO2, compared to almost much lesser. Somewhere here it is about 0.3 for TiO2 only. And for the dye, it was found to be slightly much lesser than that of quantum dot. And we find that the dye was not stable in water, but that doesn't that is not giving anything against the trend. We find that the 0.4 ND is much better than that of the TiO2. Okay, so to summarize, whatever we have worked on just came out recently. It's about a week ago. This paper is published in Solar Energy Materials, where we presented this entire story as vacancy-induced enhancement in neodymium loop titania photoanodes, based sensitized and solar cells and photoelectrons. Okay, so to summarize this entire story, we have presented a comprehensive picture correlating the physics of ND-doped TiO2 as photoanode for sensitized solar cells. Okay, the effect of ND-doping in anodized TiO2 is critically characterized using different techniques, and the role of vacancy is established. Sensitive solar cells with standard N719 dye and CDS quantum dots found to give about 30% for QDSC and 16% for DSSC. And the most interesting result was with respect to the water splitting data, where we find that the photocurrent is enhanced 3 times for when sensitizing with CDS quantum dots compared to the undoped TiO2. For dye, this was enhanced by 2 times. And overall, this sort of begins our leads to the present work which we are doing presently, where we are talking about trying to find a nice co-dopant and see how one can improve this entire water splitting as well as the band gap properties much better. Okay, so I would like to stop my talk with this presenting whatever we do in our lab. We do a lot of solar cells, as well as we work mostly on time resolved spectroscopy, non-linear optics, do a little bit of ceramic photonics, etc. I like to thank all my funding sources. Okay, this is my group, and all the work is done by this guy, Venkat. I thank you for your attention, and you can just visit our lab anytime and contact me for any discussions or other things. Thank you.
Thank you, sir. Thank you so much, sir, for your nice talk. Sir, there are few questions on this talk. First question from Dr. P.K. Singh.
Yes.
He asking, what is current scenario of organic solar cell in case of Indian perspective?
In case of?
Indian perspective, Indian.
We, okay, we are able to now, okay, let me answer you in two ways. One, the advent of perovskite solar cells have changed the entire scenario. Okay, now it is before perovskite solar cells and after that. Now, before, if you consider all the technologies which is not related to perovskites, we are there up to 10%. I have seen some of our groups in IIT Bombay, NPL, and a few here and there are able to routinely get the organic solar cells based on DSSC as well as the polymer solar cells up to 10%. There has been some improvement in a lot of chemists have contributed towards the development of the non-Freeland acceptors to the organic solar cells. Now, from the point of view of perovskites, we are now as good as what everyone is doing, because most of us are trained outside and we have come back exactly at that time perovskite revolution began. And in India, most of the labs who are working on perovskites are routinely developing, are able to get close to 20 to 22%. Okay, so from efficiency point of view, we are more or less competing with respect to the various leading groups across the world. From fundamental point of view, also we are contributing from a fundamental understanding point of view. I would say where we are lacking is slightly based on the kind of optimization. Okay, sometimes somehow our optimization is not good, and also from the point of view of non-Freeland acceptors, some more work has to be done from Indian researchers' point of view. Otherwise, we are as good as others, and India is able to compete with both in terms of publications as well as the efficiencies, as well as the fundamental understanding on par with any other leading group in the world.
Another question from Dr. P.K. Singh. What happened with band gap if we dope more than 0.5% ND in TiO2?
Okay, so if you dope more than 0.5 ND, we found that the structure of the titanium is completely changed. So in fact, we have done the experiment. We find that the solar cell doesn't work. Okay, it gives you about 0.2 to 0.3% efficiency. And from physics point of view, the XRD pattern showed that somehow the structure of the titanium is changed. New peaks are formed and everything is slowly getting degraded. And dielectric constant has become different. And overall, beyond 0.5%, the device as well as the titanium properties are all changed. So that's why we showed only till 0.4, 0.5. We have worked for 0.6, 0.8, and 1. So all these things never work.
Yeah. Okay. Sir, another question from Dr. Yogesh Kumar. Nice talk, sir. Why excitonic energy less than thermal energy in case of inorganic semiconductor and greater than in case of organic semiconductor? According to you,
okay.
What could be the easiest way to increase efficiency of DSSC relative to the current reported efficiency?
Again, two parts to this question. First is why it is less. So, as I said, it got to do with the lattice, lattice.
I think there is a technical issue.
Manish sir, I think there is connection problem.
There is a connection problem. Okay, rest of the questions, all the participants can email to the sir, and we will. I think there is a website for the sir. You can note down this website and send the questions on the email.
What is the basic idea of the Vanier mode?
Sir, unmute, please. Unmute.
Yeah. I did not know that. I totally escaped.
Okay, sir. No problem. Actually, there is.
What is the answer? Till what I could tell you. Shall I repeat the answer, please?
Sir, can you? The participants can email you the questions.
Yes.
Because the time schedule is so much packed, and next speaker are waiting.
Okay. So just to answer briefly, the answer lies in how we discuss the Vanier mode and Frenkel exciton. So if you understand these two, then the reason why it is lesser for inorganic and higher for organic comes into picture. So
Yeah.
please read it and
Thank you, sir. Thank you, sir. Dr. Arvind.
Thank you, sir, for a nice and brief talk on the current scenario of photovoltaic cell. And uh, uh, today is a very necessity of such type of solar cells which have more efficiency for the energy applications. And I think there is no more question. Participant can directly contact you via mail. And
sure.
so thank you, sir, for accepting our invitation and in this RAFM 2020. And thank you, sir.
Yeah,
Thank you.
And I
I
have
wish you all
also,
the best.
sir, I have also the question, and I will contact you through the mail.
Please, please,
Yeah.
please. I'm happy to answer you. Yeah.
Yeah. Thank you, sir. Thank you so much. Our next speaker is Dr. Avni Sansul. I think, yeah, sir has joined. I want to give sir a brief introduction about sir. Actually, he is my senior also. So first time I'm going to introduce in front of a gathering. Dr. Avni Sansul is a PhD in physics with 15 years of research experience in energy and environmental materials related research. He has worked at Technical University of Darmstadt during his PhD. He has also worked collaborations other international laboratories on materials for energy and environmental applications. He has over 40 research publications in International Journal of Repute with H index of 11 and I10 index of 12, and 7 international patents in addition to a few contributions in books. He has received a few awards recognitions for excellence in research, Young Scientist Award, and also received various fellowship in India, Nehru Fellow. He is actively involved in various rural projects and coordinating many activities of rural relevance at CSIR NERI, Nagpur. Dr. Ansul is serving as an expert member for various committees related to CPCB and other organizations. He is currently involved in more than 10 R&D projects. His research area focuses on environmental materials, 2D structured materials for green energy, multifunctional nanostructured materials for energy and memory devices, perovskite materials for photovoltaic applications. Sir, I welcome you in this scientific meeting and request you for your talk on the topic investigation of piezoelectric, magnetic, and structural properties in BFO-BST nanoparticles. Sir, please.
Thank you, Dr. Manish, for this wonderful introduction. So I want you all the listener to request that can I divert a little bit from the topic which I have already mentioned, because some of the few lectures what we have listening here is all about the heavy dose of sciences and magnetic, electric, optical properties. So since my responsibility is also towards the policy making side, I think I should go a little bit toward the environmental and policy sides of this all the functional material. If you please allow me to change my research topic from there to environmental aspects of functional material.
Yes, sir.
Can I do that, Dr.
Yes.
Machine?
Yes, please, sir. Yes, sir. Please.
So I'm sharing my. Dr. Manish, my screen is visible.
Yes, sir. It's visible.
Yeah, good morning, all of you. I'm Dr. Avnish Ansul, working as a principal scientist at CSIR NERI. CSIR NERI, one of the premier institute working in the area of environmental environment for government of India, and mostly we are dealing with all the aspects wherever the environmental comes. I can show you some of the glimpse of the what NERI is, because most of you for the first time hearing this name. NERI. So I just give you the brief introduction about our institute and what we are working, and I think you will also correlate with your day-to-day activity with the work what we are doing in our laboratory. So giving the brief introduction about the CSIR NERI. CSIR NERI we got established in 1958 when jaundice epidemic occurred in India. Jaundice epidemic इंडिया में आया था उस समय सिफेरी के नाम से गवर्नमेंट ऑफ इंडिया ने नीरी को लॉन्च किया था, where we are having the responsibility to do research on this public health and also the water mission. Then slowly and steadily the objective of this laboratory, objective of this institute has been added, and we are working from almost all the aspects of air pollution, water pollution, and also we are working as a knowledge partner for MOEF, Ministry of Environment, and also working a lot for NGT cases. So what NIRI is doing actually, NIRI is working on the area of wastewater treatment. We are working with the clean air, environmental designing and modeling, environmental biotechnology, environmental materials. Where I am actually working on the environmental materials, environmental impact and risk assessment, environmental health, environmental genomics, solid and hazardous waste management, and clean water. So you might be hearing that इतने सारे एरिया पे हम CSR NIRI काम करते हैं environment पे, फिर भी हम लोग का environment इतना damage हो रहा है. So we all are responsible for that, and the little steps what we are doing. I just want to highlight some of the few areas where we have recently done a lot. So these are the we are working in pan India projects. We are working on we are having the project almost every state of India. And we are also having the 5 zonal center of CSI NIRI at Delhi, Mumbai, Calcutta, Hyderabad, and Chennai. And also we are aggressively working on the national missions like Clean Ganga, where Namami Gange and CSI NIRI is working together, and also in the Swachh Bharat mission and Swasth Bharat, of course. Smart cities, we are having a lot of projects from smart cities, and National Highway Green Mission is there. National with the national highways, whatever the construction is going on, the parallel plantation is also going on, and NIRI is responsibly doing all that. We are also having the international collaboration on the environmental side from the India, from the almost 32 countries all over the world. We are having the international partner. We are representing India as in all the environmental forums abroad. So the grand challenges where we are working on is the river and water body regeneration. अभी जितने भी हमारे नदियां हैं इंडिया में, जिसको भी cleaning process चल रही है, for example, Ganga and all that. So we are actively working on the Yamuna River also, and we are also mapping almost all the rivers of India. वो छोटी नदियां जो कि हमारे maps में available नहीं है, जो हमारे records में available नहीं है, we are also trying to map it so that a better policy can be formulated. So basically, we all are also, beside research, we are also working on the policy making so that government should take steps and initiatives towards the clean environment systems. Climate change is always a hot topic now. We all are hearing everything in the climate change and all that. So we are also working in that area. Besides environmental big data analysis and supercomputing for solving the environmental problem, and of course the integrated solid waste management. Abhi bhi hum log, most of you are I think from Delhi and might have visited Delhi. When you are going from outside, you can see the big hills of garbage dump site and all that. So we are trying to solve it out, and of course the government is taking the very good initiatives for solving out. But the problem has been accumulated from such a long time. It takes some time to be cleaned up. And I just like to show this slide because अभी 14 तारीख को हम लोग सर्व दीपावली मनाने वाले हैं, and I am happy to share that CSI NIRI is the leading institute. अभी green firecracker का काफी नाम आप लोगों ने सुना होगा, and we are happy to say that our senior Dr. Sadhana madam is leading this project, and we have successfully demonstrated and launched this green firecracker, and Supreme Court has also given some noting that जो भी आप firecracker बनेगा, it will be from the formula given by CSI NIRI. Of course, this green firecracker cannot solve 100% of the solution, 100% of the pollution what we are getting. But of course, we have worked on the formulations, we have worked on the formula, and we have worked on how this material is being firecracker is being made. So to make it more greener, we have almost absolute the use of the heavy materials so that SOx NOx percentage will be reduced, particulate matter should be reduced. The formulation has been changed. तो अभी दीपावली में जब भी आप पटाखे फोड़े और ग्रीन पटाखे में आप होलोग्राम जब आप स्कैन करेंगे, then you can I feel happy जब आप देखेंगे कि वो CSI NIRI का डेवलप किया हुआ ग्रीन पटाखा है. Similarly, we have also worked on a lot of other projects. जैसे अभी हम लोग ने रिसेंटली कुंभ हुआ था फरवरी में, जब हम काफी न्यूज में ये आया था कि गंगा रिवर के पानी साफ हो गया इस बार. कुंभ was better organized, water was more clean of the Ganga and all that. So we were also contributed a bit in that. हम लोगों ने ये नमामि गंगे के साथ लिया था, and we have treated all the drains of whatever falling in that Ganga river and made that water clean. A lot of other agencies have also worked, and we also contributed that to make that Kumbh a successful and holy festival. And we have also got a lot of appreciation and national award for working on that clean Ganga mission during Kumbh. एक आध एग्जांपल मैं और देना चाहूंगा. फॉर एग्जांपल हम लोग एक अर्बन कैरिंग कैपेसिटी पे भी काम करते हैं, जिसपे हम लोग ये बताते हैं कि किसी भी सिटी का कितना कैरिंग कैपेसिटी होनी चाहिए. फॉर एग्जांपल दिल्ली इज बर्स्टिंग. दिल्ली का पॉपुलेशन इतना ज्यादा है कि वहाँ के जो लोकल रिसोर्सेज है इट कैन नॉट सस्टेन. तो सिमिलरली अदर सिटीज ऑल्सो. एक छोटा सा एग्जांपल है, जब हम लोग राष्ट्रपति भवन जाते थे, वहाँ पे मुगल गार्डन देखते थे, देयर वाज अ लॉट ऑफ क्राउड. So earlier, it was affecting the ecosystem and also the plant species, whatever lying there, and plant species and all the other environmental aspects. Then, on the basis of the NIRI's report, that their Mughal garden of Rashtrapati Bhavan is being taken care in the well manner. And हम लोग ने उसमें restriction दिखा दिया कि एक दिन में इतनी carrying capacity है, इतने लोग यहाँ पे visit कर सकते हैं, so that it can be good for the next generation coming. इसी टाइप के हम लोगों ने बाकी हिल स्टेशन, टूरिस्ट प्लेस, wherever is required, we are working for the carrying capacity for the cities. जो भी new smart cities बन रहे हैं, how we are going to minimize so that the environmental sustainability should be maintained. So environment economics also we are working on. ये सारे कुछ areas हैं. This is also new area which we have studied. Sometimes we people are thinking that कि कोई भी environmental damage हुआ, किसी भी company ने कोई environmental breach किया, for example कहीं कुछ उसका waste पानी में बहा दिया, then how much should be damage in the of environment in the terms of economics? कितने उसको हमको charge करने चाहिए, how much we should charge them, how much fine should be there. These are calculations we are doing for most of the judiciary hearings. For example, यदि कोई कहीं कुछ बाढ़ आता है तो कितना डैमेज होता है, सरकार को कितने मुआवजा देना चाहिए. These all calculations we are doing for the government of India and also the state government. Now coming to the topic. So we all having here the eminent researchers who is going to give the heavy dose of the science. It's making a lot of electric, magnetic, and optical properties on which all the functional devices are working. You will be hearing, and similarly, very active and very vigilant audience are also available. जो बहुत सारे questions पूछती है और बहुत सारे research ideas इस type की meeting से generate करते हैं. I just want to sensitize this type of gathering with some of the few activities. When we are talking about the functional materials, when we are talking about the nanomaterials, there are a lot of environmental aspects also, which we should keep them in our mind while developing, so that a new and sustainable things should come up. हम लोग एक ऐसे जनरेशन के towards बढ़ सके जहाँ पे हम लोग बोल सकते, जहाँ पे हम ये बोल सकते हैं, जो हमारा मटेरियल जो डेवलप किया है हमने, जो हमारे जो ये प्रोडक्ट डेवलप किया है, it's very environmental friendly and it is sustainable. Since we all are working here for the development of new type of materials, and we all know that functional materials has applications, a lot of applications in for medical purposes, electronics and information system. We have already seen that lot of electronic device which we are working on, and and personal care products, cosmetics जो भी हम लोग use करते हैं, they are also having the nanomaterials and the functional materials. And agriculture is not less now. Agriculture farmer is also looking for some of the hybrid seeds, hybrid fertilizers to enhance their crop productions. And application of application of these functional materials in water purification is well known. Most of us are using the ROs and the filtration system in our house because of the water quality what we are having. And food safety also we all know that from the field to dining plate, everywhere this functional material, this nanomaterial is being used. Cleaning agent, जब हम लोग इसी nanomaterials use करके, हम लोग chemicals use करके, हम लोग एक तरफ कोई product develop करते हैं और उस चीज को damage करते हैं, then again we are cleaning it with using same type of functional materials. So I just want to highlight some of the few points कि हम लोगों को जो भी device develop कर रहे हैं, it should be sustainable, it should be environmental it should be compatible to the environment, so that it's from the after few generations we should not feel that कि अरे यार ये just like plastic, यदि प्लास्टिक को हम लोग सही ढंग से इस्तेमाल किए होते, प्लास्टिक is of course a beautiful product which we all know, we can make anything out of it, but when we are moved toward the application of the plastic, it's really horrible, and it has become a problem for us. So similarly, what I just want to synthesize this gathering here to think and develop the material which is sustainable and which is environmental friendly. Medical application, we all know that from the disease treatment to the drug delivery, we are using these functional materials. Electronic information system we have already discussed, and also in the metal oxide nanometers in the cosmetics and products, farmlands, nano application, in the water purification, everywhere we are using. Now the material technologies and challenges. Where are the challenges we are facing? What are the points what we should look about while developing this functional material is? The functional materials is in the present is a unique and risk for the health. We all know we should have to take care of this at the beginning of the thing. If you are using a lot of heavy metals which ultimately going to harm our environment, we should look for the other alternative, because you are the highly eminent researchers. If you are keep this point also in your mind while developing the new product, you can choose the material, you can choose the elements which is not going to harm in the future, which can be easily tackled. We should avoid the use of the heavy metal. Of course, there are places where we cannot avoid, but we can limit the applications of this type of element which is going to harm in future. The potential benefit of the functional material also functional materials by minimizing the potential risk. This is the important point. We have to do the risk analysis of the product what we are developing. Not only in the techno-economic feasibility which we already doing. That कि हमारा जो product develop होगा तो वो इतना economically cheap होगा, हमारा इतना functionally better होगा, it can do this much fast job, इतना speed बढ़ जाएगा उसको. Rather than other potential risk also we have to take care. That is the risk of the environment. Whether in future is it going to have any risk on the future environment also. Functional materials have the low dispersion stability, prone to their accumulation and leaching through membranes-based nanofilters. So whenever we are using any product, for example, when we are using any product nanomaterials for in cosmetics, जब हम लोग बाथरूम में wash out करते हैं, जब हम लोग नहाते हैं जो wash out हो जाता है, तो क्या वो nano particles accumulate हो जा रहा है, क्या वो nano particles environment में decompose हो रहा है कि नहीं? So it is very small thing, and government is not taking care of all the aspects because we all know that environment we cannot ignore. Another issue is sustainability. Suitable modifications are needed for effective utilization of technology for the surface and water treatment. Water treatment is really a challenging thing. I have just shown one of the example where we have worked during Kumbh and also working for the all the major drains in Delhi and all over the India. Delhi में भी जो 5 main drains हैं जो कि यमुना नदी को खराब कर रही है, we are also working there. So can we look for some of the technologies which can be environmental friendly? हम लोग environment से कुछ solution ढूंढ सकते हैं क्या? And I'm happy to say you this, जो भी हम लोग जो टेक्नोलॉजी हम लोगों ने करोड़ों में ट्रांसफर किया है, जो कि कुंभ के समय में यूज हुआ था, and we are going to use there in Delhi and most of the other UP and other states, Jharkhand and states, to clean the rivers. There we are not using chemicals. We are using environmental plants. Like जो plants heavy metals को absorb कर रही है, waste water को उसको treat कर ले. So can we have such type of environmental friendly materials which can be used as a functional materials for advanced applications? Functional materials have the toxicity concern for the human and animals. We all know जब वो हमारे जब water में wash out होते हैं, जब हमारे soil में जाते हैं, then it's coming to the food chains, and we all know what are the concerns it is doing, and concern is there for our health. So these are the few points which I just want to highlight with this eminent audience. And these are the do's, the functional materials and what should be done. So we have to provide the hydraulic control of the experimental side. We all have the laboratory where we are using the chemicals and heavy metals, or the industries or the plants or treatment plants. There has to be some hydraulic control of the experiment setup. जो भी हम wash basin में wash out करते हैं metal water, it should be hydraulically controlled so that all the heavy metal, it should not go the environment back. It should be filtered out and it should be treated properly as per the norms of the CPCB, as per the norms of the government of India or state government. So this type of proposal we have already proposed, so that most of the industries they are putting that centralized water treatment plant, or if the plant is very big, they are also having their individual water treatment plants. So CPCB and all the other government agencies is also strictly looking for the compliance of this type of activities from the industries. And also in our small labs, जब हम लोग छोटे-छोटे labs में काम करते हैं, where we don't feel ये बहुत ज़्यादा important है, there also we can have a small challenge, because we all are here as a scientist, we all are doing experiment in our laboratories, and we all are doing most of us are doing same type of mistake. So compromising the real and lab environments should also be done, providing the practical data of the nanomaterials for the policy making. So most of the people's as a researcher we are saying here that जब हम लोग कोई material या कोई भी product develop करते हैं, तो we are not providing we are just talking about the enhance of the properties. कि हमारा ये इतना अच्छा property हो गया, we can have this much of connectivity, we can reduce this much of coupling, this and this that. But we are not awareing the people if when we are using this type of nanomaterial can have this type of effect also. Or after utilization, this can be this has to be disposed like this also. We are not taking care of that. That part is also, I think, is a responsibility of the product developer or the responsibility of the scientist to educate the people who are the end user of this material, and also for the policy makers, where I am also the part of it, so that we can have the better understanding of the nanomaterials, and we can sensitize the end users for the application. For example, solar cell. We all know we have to look for the solar cell. We all know that. But once the solar cell is loses its life, then how to reuse it, or how to disintegrate it, or how to dismantle it. I mean, so हम उसको कैसे खत्म करेंगे? Then it should not be accumulated as in a hill. We cannot. So वो part also we have to take care, so that policymakers should say this type of things we can do. So and the benefit of the sustainable functional material, we all are working here for the enhancing the property. We should also look, one of the aspects that whatever the functional material we are developing, it should be sustainable for the future also and the coming generation also. How we are going to do this? How we can understand this functional material is sustainable or not? How we can say our material, the material what we are developing is environmental friendly or not? How much, whether it is creating more harm or reducing the harm with the conventional material. For this, we are doing in our laboratory the life cycle assessment of the functional material. So life cycle assessment people are doing. So it is from the cradle to gate and or the cradle to grave. So cradle to gate जब हम लोग raw materials कहीं से dig करते हैं, वहाँ से लेके जब product factory से बाहर निकलता है, everything we are considering. यदि हम raw material लेने जाते हैं, then how much ट्रांसपोर्टेशन इज रिक्वायर्ड, वहाँ पे कितने लेबर काम कर रहे होंगे, कितना ट्रांसपोर्टेशन काम कर रहा होगा, यदि वहाँ माइनिंग हो रही हो तो कितना इमिशंस होता होगा, यदि वहाँ ड्रिलिंग हो रही हो तो कितना इमिशंस होगा, यदि वो मटेरियल ट्रांसपोर्टेशन से इंडस्ट्री तक आई तो वो ट्रांसपोर्ट का इमिशन कितना होगा, ट्रांसपोर्ट इंडस्ट्री के अंदर जो ट्रांसपोर्टेशन हो रहा है उसका इमिशन कितना होगा, इंडस्ट्री के अंदर भी इलेक्ट्रिसिटी और फैक्ट्रीज चल रहे हैं उसको मेंटेन करने के लिए उसका इमिशन कितना होगा. And not only air, water, everything, water balance. We are calculating everything from the cradle to the gate. जब वो फाइनल प्रोडक्ट बन के आता है, देन वी कैन से ये पूरा प्रोसेस में ये प्रोडक्ट बनने में इतना वाटर यूज हुआ, इतना कार्बन डाइऑक्साइड इमिशन हुआ, इतना सॉक्स हुआ, इतना नॉक्स, एंड वी कैन इतना ओजोनिफिकेशन हुआ. वी कैन हैव द ऑडिटेड फिगर ऑफ एवरीथिंग. देन वी कैन फाइनली से कि हमारा जो कन्वेंशनल सिस्टम था उसमें इतना इन्वायरमेंटल डैमेज हुआ और हमारा जो न्यू फंक्शनल मटेरियल जो हमने डेवलप किया उसमें इतना कम कार्बन डाइऑक्साइड इमिशन हुआ. सो So this is the and if that material product what we are developing is going to be reused, or it can be becoming the source for the other industry, जो प्लास्टिक है चाहे कुछ भी है यदि वो हम कहीं और तोड़ के यूज कर रहे हैं, तो देन आल्सो वी कैन हैव द क्रेडल टू ग्रेव जब तक वो फाइनल डिकम्पोज नहीं होता. वी ऑल we do the calculation through life cycle assessment of this material develop, of the process develop, which is coming to the ministry, which is coming to the government, saying that we want to have this type of plan to set up. We can do all this assessment and give the final report, saying the government this is the emission being made by this type of material, this is being made by this type of product, whatever we are making. So through this life cycle assessment, there are few software. We are using the Gavi Pro software, and of course Gavi Pro software Indian database we are using, where जहाँ पे हम लोग इंडिया का रोड कंडीशन, जहाँ पे हम लोग इंडिया में ट्रक्स के emission levels का database है, उसको हम लोग यूज करके ये सारे कैलकुलेशंस करते हैं. So environmental risk and risk concern, of course, we know what happened when the functional materials or the product is getting disposed. Getting disposal. हमें उस चीज पे भी ध्यान देना चाहिए कि हम सोलर सेल बनाते हैं, and तो उस सोलर सेल को जब लाइफ एंड हो जाता है तो how we are going to dispose that. People are working on the disposal of solar cell, and I can tell you most of them are working that they are using the chemicals to disintegrate the metals from there, and that chemicals which they are using to mix and extract that material is going to be fatal for the environment. So we have to look for some of the sustainable solution for this type of waste disposal also. What is the fate of the environmental material after it degrades? Whether it after degradation it is going to become neutral, whether it is again going to harm the soil, again going to harm the water, again going to harm underground water. It is also the matter of concern which we are looking at the policy level. Whether this material after getting accumulated in the food chain, यदि हम लोग ज़्यादा chemicals use करते हैं, ज़्यादा चीजें use करते हैं, whether it is coming to the food chain or not. So now you can see in the food packet is also it's mandatory to say कि हमने किस type का preservative use किया था, हमने किस type का chemicals use किया. It is mandatory now. So government is very much focusing about all the health concern of the people now, and we are working on the policy. So risk assessment framework for the functional material is also required to be made beside this regular, and have to identify the characteristics of the material what we are using, whether it is hazardous or not, and of the raw material. What are the process we are doing? That process is sustainable? Is that process is emitting more carbon dioxide or damaging more to the environment? And what are the product? What are the packaging system we will be doing? And what will be the end use? So this type of risk assessment and framework is, also need to be focused while developing this functional material. And also, if that material, while formation of that material, whether it is industrial feasible or not, whether what type of precaution industry people should take while manufacturing at a higher level, what type of means equipment should be used, what type of precautions, what type of fire hazards, everything we have to make, and as a complete package. And it's a bit surprising that India is not having any, till now India is working on it, but we don't have any federal agency which is accessing this functionality and the environmental aspect of the nanomaterials. But of course, in EPA, we are also having the toxic, abroad we can having a lot of these agencies who are working for the countries as nanoparticle information library is there, what type of nanomaterial is there. So this type of food and drug administration is taking care of food and drug and cosmetics. So विदेशों में ऑलरेडी ये पॉलिसीज एंड ये एजेंसीज बना दी गई है जो कि हमारा फंक्शनल मटेरियल, हमारा नैनो मटेरियल के एप्लीकेशंस को सर्टिफाई करे, वेरीफाई करे whether it is harmful for the environment, harmful for the people or not. So assessing the risk for the functional material is the key for all the research and development activities what we are doing. So identifying and the characteristics of the material, whether it is hazardous or not, in the assessing the potential exposure scenario. यदि हम हमारे materials यदि वो टूट जाता है, damage होता है, accident होता है, then what will be the scenario? क्या उससे कुछ problems तो नहीं होगी, ecosystem damage तो नहीं होगा. And evaluation of toxicity for the functional material, whatever we are developing, is also the key for this. Characterization of the risk and uncertainty. So this is mapping also is a part should be the part of the research what we people are doing, and communicating the risk to the policymaker and highlighting the risk also while developing the products. It should be the key for our research in the area of functional materials. So thank you so much. This is all I just want to say to this eminent committee.
Sir, thank you so much for your nice talk on environmental. It's much more necessary, not only India, not only in Delhi, but whole India. Sir, there are some questions from participants. Dr. P.K. Misra from Nainital.
Yes, sir.
Whether data on river size and location, etc., available on website as an archival data?
So we are Government of India is running a Jigyasa Jagriti program under which we are mapping all the river bodies, small and big. So hopefully we will be having a database where we can we are having the mapping of the water quality, we are having the mapping of the size, we are having all the characteristics of the water bodies available in India, even in the small rivers which is not being mentioned in the data bank right now. So we are already on it, and we have covered around 12 states, and the final data will be launched soon.
Second question from P.K. Misra. What is the current status of connecting various rivers of our country?
So it's a part of the policy making. So it's I don't know exactly what is the status, and we are always given the task that ये water bodies में इतने problems हो रही है, what type of solution we can approach for. So we are as a scientist, we are just telling the solutions or approach to tackle the problems and propose the solution. But we don't know exactly about the joining of the river and all that. Of course, it's a hot topic, and government definitely might have to think about it.
Thank you, sir. I think there is no question. Dr. Arvind? Dr. Arvind? Dr. Arvind is not there. Then, okay. Sir, thanks a lot, sir, for your nice talk on the environment. And I think there is no any other question in the chat box. If we have any question or query, we will mail you. I will provide the email of to our participants. And I think...
yeah, yes, Manish sir, I am here.
Yes, yes. Please.
I am here.
Please continue.
Yeah, thank you, sir, for such an informative talk. Finally, I would like to take this opportunity to heartily thanks to you, sir, in this RAFM 2020 for the perfect logistic and optimistic approach towards the environment in your talk. I also extend my thanks to you, sir, to discuss the impact of materials in view of our environment. You have shown us the second perspective of the functional materials. And once again, I thank you, sir, for accepting our invitation. Thank you, sir.
Sir,
thank you so much.
I hope, and I also invite you for all the sessions and validatory function also. I will call you personally for this validity function also.
Thank you so much.
Thank you, sir.
Thank you.
Our next speaker is Professor U.P. Singh from KIIT, Odisha. Sir has joined. Dr. Amit?
Yes, I am here.
Yeah, sir has joined.
Okay. Thank you, sir. Thank you. I want to give some brief introduction about sir. Professor Uday Pratap Singh has has nearly 25 years of experience in teaching and research. After completing his PhD from Banaras Hindu University, Varanasi in 1993, he joined Global Solar Energy India Limited, Gurgaon, to work on the process development and production of CDTE-based thin film solar cells. In 2000, he joined the Institute of Energy Conversion, University of Delaware, USA, as limited time researcher, and worked on the process development of flexible CIGS-based thin film solar cells. He joined KIIT in December 2002 as a faculty, and currently he is senior professor in the school. During his stay at KIIT, he has been visited as visiting consultant of Industrial Technological Research Institute, ITRL, Taiwan in 2008 and 9. Dr. Singh has developed a good research facility in the area of thin film photovoltaics from several research funding forums, DST, DRDO, MNRE, etc. Dr. Uday Pratap Singh, senior professor in the School of Electronics Engineering, KIT deemed to be university, had participated and completed the leadership academician program sponsored by MHRD Government of India from 23rd September to 5th October 2019 at Banaras Hindu University, Varanasi, and from 7th October to 12th October 2019 at NTU, Singapore, Nanyang Technological University. In all, 25 participants were selected from all over India to participate in this program. He has guided so many PhD students. Currently, he has administrative responsibility as Dean Research at KIIT. Sir, I welcome you in this scientific meeting and request you for your talk on the topic recent developments in thin film photovoltaics. Sir.
Okay, thank you for giving a nice introduction. Thanks the organizer for inviting me to give a talk at this forum. So, as I have seen your program, so it's a wide spectrum on different areas. So I have kept my talk general. I will not be focusing on any particular much detail like physics-wise. So I have kept it general talks like it will be interest for all the audience. So as you have told in introduction, like my area of work is basically on the thin film photovoltaics. Okay, so you know, like crystalline silicon is the most popular, and everybody knows about that crystalline silicon. So we have moved to the, and I think in the earlier talk, like from Dr. Ravi, from like he was talking about TiO2, and then for the dye sensitized solar cell. Nowadays, like most of the people have moved to the perovskite. So I'll not be talking about the perovskite. So let me start. I am from the KIT Bhubaneswar, which is the deemed to be university and Institute of Eminence in the MHRD ranking also. Okay, so so I'll just briefly introduce like so basically what is photovoltaic, and then so among a wide variety of renewable energy projects, photovoltaic is basically the most promising as a future energy technology due to pollution free. The input energy is abundant, available everywhere. That is the sun. It's also operated by in the diffuse light. People are working for different solar cell like that can expand the span like from dawn to dusk. Only problem was the high price of the solar module, but like in recent year, if you have seen, like the China has increased the production, so the cost has now come down for the silicon also. Earlier, the cost was a major concern, but so due to this cost, like people have moved to some other alternative so that the cost can be reduced. So the cost reduction of solar cell is very important. Like if you want to compete with the current electricity. So history-wise, if you see, so most people are familiar with the like which has been discovered in 1954, the Bell Labs, where they have shown like silicon, if you do with certain impurity, was very sensitive to light. But earlier to that, also in 1883, there was first solar cell built by Charles Fitts, who basically coated this semiconductor selenium with the gold, and it has given around 1% efficiency. Okay. So, but most popular because the breakthrough came in 1954 when the Bell Labs discovered that silicon. So if you want to look for like what are the ideal solar cell material, so people are looking a band gap of between 1.1 to 1.7 electron volt so that it can cover the whole spectrum. It should be a direct band gap structure, but you know silicon is an indirect band gap structure consisting of readily available non-toxic material. If you are going for any other new material, you try to see like it should be non-toxic, because like Dr. Avinash Anivesh or Avinash Niri, he was talking about like after a certain time you have to dispose this material. Like if your solar panel is working for 15 years, 20 years, then there is a problem of disposing. So if it is a non-toxic material, then it is good. If it is a toxic material, then you have to use certain chemicals, and then how disposal is become a big problem. Then one need easy reproducible deposition technique suitable for large area production. good photovoltaic conversion efficiency is matters, and then one looks for the long-term stability. Like if you are making like silicon cell, solar cells, people are giving warranty for 20 years, 20 plus years. Maybe there may be some, they give with the certain reduction in the efficiency, but the stability is like they give the warranty for 20 years. So if you one look for the efficiency, basically it's the fraction of incident light energy converted to electrical energy. And efficiency is the most important part because it allows the device to be accepted economically in comparison to other energy another devices. Because if you see, if you get it cheaper than the household electricity, what is coming from the grid, so people will try to buy the solar. And from the given solar spectrum, the efficiency depends on the one is the semiconductor material, other is what device structure is one going to form, ambient condition, what temperature, like if you go to European countries, like sunshine is limited, high radiation damage, like if you are using for the space application, then one has to look for like it should not be damaged by the high radiation, sun spectrum. And so efficiency alone is not enough. Cost of the cell is also important, like and the lifetime. So cost and lifetime is also important as well as the efficiency. These three are the major factor when if you are looking for some other new material. So in this case, there are many approaches to making PV cells, and experts basically don't agree like which one is the best. Like if somebody is working in perovskite, they will say like perovskite is best. If somebody is working in CIGS, they say like. So it's basically a competitive market, but still silicon holds the major part. Still more than 85 to 90% are crystalline silicon. One can have the concentrated photovoltaic also because it takes the cost and space. So yeah, so I will be focusing on thin film materials and mostly on the copper indium gallium selenide, which is my area of work. And people are working for the dye-sensitized solar cell or organic solar cell. Now people have moved to the perovskite. Like a lot of in this second last lecture, somebody asked like, what is the status of solar cell in India? Because like if you want to work on the research level, you always look for the funding from the government. So only problem with the funding with the government is that like if you get a project for 3 years and after 3 years, it's stopped. So from where you get it, so you cannot extend. Like some funding is given if somebody has progressed, they may get some another fund so that they can come with certain product, because it's not very easy. Like if you work for 2 years and then you can say like, sir, you have got the efficiency and we'll work. So one needs a continuous funding to produce certain thing. That is one of the biggest problem for R&D sector in India. So why crystalline silicon is so successful? Because it's a high module efficiency up to 20% one can get, but regular way can have a 17 to 18%. High stability and reliability, mature and modular technology is there, and there is no environmental concern because silicon, like if you want to depose it, silicon wafer is made from the silica, that is the sand. Okay? And then there are certain other chemicals are used, like some silver paste or the EVA, like this polymer coating on top of that. So that can be disposed of easily. Wide material availability, there is no concern for the material availability for the silicon. So if you are going for new material, so a similar advantage must be possessed by the competing material. Then only you can compete with the other. It's a valid for anything. Like if some material is already available and is cheap, so if you want to discover, want to compete with that, then you have to make cheaper or maybe competitive with that. So only weak point with the silicon is like you say, direct band gap, so low light absorption coefficient, and basically the cost. But now the cost has come down drastically. Now moving to thin film. So if I'm interested for thin film, so it has to compete with the established crystalline technology, any thin film photovoltaics, to achieve comparable performance with the promise of substantially lower cost, and then the high production capacity with reduced material consumption and energy input in the fabrication process. The other thing is energy payback. There is one term used is energy payback time. Like how much energy you are using to produce the cell and in how many years you are trying to get that value. Okay, but for silicon, generally it takes 3 years. The energy required to produce and then to recover that value. Okay, but like if you're going to thin film, the energy paid by time is basically 1 to 2 years. Lower module cost for large area terrestrial applications. So advantage of thin film, all the thin films are like thin layers, 1 micron enable to low material cost. Continuous large area manufacturing is possible. Cell interconnects are produced monolithically. Like if you see the silicon, they are different modules. Then you have to, different wafers. Then one has to interconnect them. But here you can deposit on a large area. Then it can be one can interconnect monolithically. Flexible and lightweight modules can also be produced. And thin films modules are aesthetically superior for the BIPV application, that is the building integrated applications. Applicability in roll-to-roll deposition is also possible. And also now people are going for the tandem application, tandem solar cells. Like it's on the research level, not in the production. So if you compare like crystalline silicon, if you have 100 micron thickness, but in thin film you can have within 1 to 5 micron can be used. So material cost is lower for all the thin film. So earlier that amorphous silicon and the microcrystalline silicon was there, but now amorphous silicon has now been mostly stopped because its efficiency could not go more than 9%. So cost wise, it's not effective. So most of the industry on the amorphous silicon is now closed. Other materials, the cadmium telluride. Cadmium telluride, only major company is your First Solar, which is producing the module. Actually, it was thought like it is include the cadmium, so it is toxic. But when the cadmium telluride is found, it's a compound. The compound is not toxic because they have shown that, and they have the First Solar. They have a buyback policy. Like after 20 years, they will buy back your module. They have the recycling plant also. Okay, because in nickel cadmium battery, everyone is using more cadmium than these solar cells. And then like where I will be focusing is copper indium gallium diselenide solar cells, which efficiency, and now it's improved to 23.4 on the research scale, research lab, and then module is basically 13 to 20. But market share is still 2%. You see this, this is the data for all the solar cell available on the NREL. So it may not be very clear, so I will just focus on the thin film. So if you can see like 23.4 is for the CIGS, and then cadmium telluride is 22.1. That is the maximum lab research scale efficiency which is obtained. But if you see the perovskite is around 25.5 on the small area. This is the data latest from September 20. So if if you look for the CIGS, I have told you like now the new material has also come, copper zinc tin sulfide, where people have tried to show like these are non-toxic and earth abundant material, but the efficiency is still limited for them. So like lab scale 20.6, and this has been achieved, let's say 4 or 5 years back. So those who are still working on this, they are not able to achieve more. There are a lot of other problems in this material. So if I see the cadmium telluride and CIGS have a potential to reach cost-effective PV generated electricity, and they have transitioned from the laboratory to the marketplace. But only the transition from lab to manufacturing has been more difficult, like what has been anticipated. So why CIGS? Okay, I will just focus more on the CIGS. Highest record efficiency 23.4 on the glass, and on the polyamide substrate also like 20.4. This is on the research scale. So if you see the mini module, highest efficiency is now 19.2. These are, and then because this thin film we can deposit by different methods. So if you are one deposit by the sputtering, it has been 16.7. Co-evaporation, which has now 22.6, to it has moved to 23.3. CIGS cadmium free. Like when you make a PN junction, mostly the CIGS is a P-type material, then you make N-type cadmium sulfide. So like Japanese and European, most of them don't want to use cadmium as a toxic, so they are trying to use cadmium free N-type material. So they have also shown like the efficiency, maximum efficiency can reach 22, and the polyamide substrate is 20.4. This is the 19.2, which is achieved recently in 2019. This is again showing the different companies which we are working on this. So I will just try to skip this. So how it has progressed, like if you from 75, crystalline silicon is almost about 24, 25. Okay, in the lab scale, more than 20. Now it is 25, between 25 to 26% lab scale. And this CIGS, which has started with 75, now it has gone into the about 20%. Okay, that is for the lab scale. So it has shown different process. There is the Boeing process was used earlier. I will show in the next slides. And then there was NRE developed a 3-stage process, which has reached nearly 20%. And then using 3-stage process, and there is the alkali post-deposition treatment, which has given more than 20% efficiency. So if you look at the material, it's basically copper indium selenide, and then if you replace some of the indium by gallium, you have the copper indium gallium selenide. So it is a compound semiconductor using 1, 3, and 6 compound. It's a heterojunction solar cell. Silicon is a homojunction solar cell. I think Dr. Vinod in this keynote, he has talked about the heterojunction and the homojunction. So silicon is a homojunction solar cell because same material is used, but heterojunction means CIGS and P-type, and then you have N-type material, cadmium sulfide. High efficiency, more than 22% is achieved, and nearly 16% large area modules. Very good stability in outdoor tests, and then you have different applications. So it's a copper-based chalcopyrite is a structure, and we are replacing some of the indium by gallium, so you get a copper indium gallium selenide. So one can vary the band gap. Like copper indium selenide is one electron volt, but if you vary this, replacing some of the indium gallium, and also one can replace the selenium with the sulfur. So there is a wide variety of band gap variation one can achieve. If you look into the material properties, so it's a direct band gap semiconductor. Band gap, one can go from 1.04 electron volt to 1.68 electron volt. High absorption coefficient, absorption length is more than 1 micron. Minority carrier lifetime is several nanoseconds. Electron diffusion length is few micron. Electron mobility is also high for this. So only like some only problem with this, like most of the time it is deposited around 500. If you see the phase diagram, so copper that has a very narrow band of around, copper should be within 22 to 25%, 24%. If it is 25%, so it becomes highly conducting copper diselenide. Okay, Cu2Se is a highly conducting, so your device will short. So optimum range for thin film solar cell is around 22-24 per atomic percent. So one has to control this during deposition by any method. Possible at growth temperature of 500 to 500 degrees C. But now for like polyimide films, which can special polymer is used like EPLEX, which can go to around 420 or 430 degrees C. So lower temperature also they can make. Okay. Another, like if you go below 22% of, then you have different other phase, defect phase like copper indium 3, selenide 5, and there are other vacancy which will reduce your efficiency. So one has to be within 20 to 24% of the copper. Okay. So when you are replacing indium by gallium, so maximum replacement is around 20 to 30%. When you go into gallium to gallium plus indium ratio goes beyond 0.3, again there is a problem. Some defect states are forming, so your efficiency decreases. So you are again limited by replacement of indium by gallium to 20 to 30%. And lately the people have shown, like if you incorporate sodium, because most of the time it is deposited on the soda lime, plain soda lime glass, which is used in the window. So some sodium diffuses from the soda lime glass to this, and they have shown different better morphology, passivation of grain boundaries, higher p-type conductivity, and so they have increased the efficiency. So as I told you, like if you are varying the band gap, so you can, if you're trying to replace, you can vary the band gap of this if you're replacing indium by gallium. So high optical absorption, direct band gap, complete correction within 1 micron. If you see this, compare this silicon. Okay, if you see the silicon, if you have 100 micron thick, then only you can absorb most of the more than 90% of the light. But if you have CIGS or CDT, you can see like if you have 1 micron, you are able to absorb more than 90% of the solar spectrum. So here you are limited with the material, and then also like physical handling is also there. So most of the time it is thickness is 120 to 150 micron for silicon. The basic solar cell structure. So how many time I have? So I think just let me know 5 minutes before so that I can try to finish it. So typical device structure is basically have a substrate, and then you try to deposit the moly. Molybdenum is deposited as a back contact. Then you have the copper indium gallium diselenide, which is generally referred as the absorber layer, where most of the light is absorbed. Then you have the buffer layer, cadmium sulfide, which is also, and then you have the transparent conducting oxide, which is referred as the window layer. And then on top, you can have some finger contact to collect the charge carriers. So there are different methods. Like if a back contact of moly is generally deposited by the sputtering, and then you have the absorber deposition. So different techniques are used. You can have a co-evaporation, you can have sputtering, and then followed by selenization. Then one can use a nanoparticling, then print it, and then selenize. Electrodeposition are also possible. Then this is the p-type material. Then the n-type material buffer layer can be deposited by the chemical bar deposition, which is very cheap. Like most of them, people are using cadmium sulfide, but like Japanese and European, they don't want to use cadmium, so they are using the zinc oxide or indium hydroxide. Then on top, there is a certain layer of zinc oxide ITO for the as a transparent conducting oxide that is used deposited by sputtering or the MOCVD. So I will just skip this. So one, if you are looking for the back contact, so what is one always think like what is the requirement? So it should be chemical stable in Selenium atmosphere. So should form a good ohmic contact, and then adhesion and structural stability. That is very important adhesion. Like it should, when you are depositing on certain substrate, it should not peel off after a certain time. Let's say after 1 year it peel off, then there is no stability of your solar cell because you have to give the warranty for 15-20 years. Stability is must. So that is why the moly stable at processing temperature of 500 to 550 degrees C, resistant to align with the copper and indium, form the low contact resistant to CIS, conductivity do not degrade during processing. So it's basically, it's a bilayer deposition. First layer at high argon pressure and second layer at low argon pressure, just to manage the stress between the two bilayer. So if you are trying to increase this argon pressure, and then, so there may be like, if you are trying to have 5 millitorr, 8 millitorr, 12 millitorr. So 12 millitorr, then there is certain crack. So one has to be limited. First layer is 5 millitorr maximum one can go, and then the second layer deposits even lower pressure. So this is a typical bilayer structure of the moly, which we are trying to deposit. We are depositing at our lab with the DC and RF sputtering. Then one look for the co-evaporation of, there are different methods. I will be focusing on two. One is the co-evaporation, where you evaporate all the 4 materials simultaneously, like copper, indium, gallium, selenium. You keep copper, indium, gallium, selenium inside this, and you evaporate all simultaneously. And there is a substrate which can be heated up. Okay. So vacuum can try to have a pressure of around 10⁻⁶ star. This is the sputtering system what we have in our lab. So you can see these are the 4 sources. Okay, so 4 sources. So you can have a copper, indium, gallium, selenide. So different. In this we are controlling the flux with the temperature. So one has to optimize. If you have some thickness monitor, that's okay. Otherwise, if you don't have to have thickness monitor, then you have to optimize. It all depends on the what is the funding. Okay, if you have a good funding, then you can have your sophisticated equipment. If you don't have good funding, you have to go with that only. So this is funded by the DST under the Solar Energy Research Initiative program. So different variation is also possible, like I have shown earlier. So initially when it was developed, started 1980, so we have the selenium throughout, and then indium, gallium, and copper, they are being deposited simultaneously. So that is has a constant band gap. So it was modified to as a bilayer, or it's referred as the Boeing process. The Boeing company has devised that. Here also, like selenium is constant throughout your deposition. Only thing what they have done, like initially they have a high copper and then low indium and gallium. So they have tried to, and further they have tried to reduce the copper and increase indium gallium. So they have a normal grading of this. But NREL has given 3-stage process, which is now being used. In first stage, there is no copper, only the indium gallium, and selenium is always there. In second stage, they have reduced indium gallium, they have increased the copper. In third stage, then again they have reduced. So they have got a double grading structure on this. So other method is the annealing and stacked elemental layers. So substrate soda lime glass coated with moly, and then deposition of copper indium gallium layers by sputtering. Then they deposit selenium layer by evaporation, and then rapid thermal process they used. Okay. So only thing, like during this, they use the hydrogen selenide, which is very toxic. So some alternative, people have used some alternative to avoid this hydrogen selenide by depositing selenium on top of that and then annealing. This is the best device which we have got in our lab, around 11% through one of the MNRE project. So if you look, I have some time, or Arvind?
You can, with 5 to 10 minutes.
Okay. So if you see the overview of CID deposition technique and the companies which are using them, so that on this top, it says different methods: co-evaporation, sputtering, electrode deposition, and printing. And this is on deposition on the glass. So these companies are doing this. Now most of the company have closed down, but are merged to form some big company. And then there is a roll to roll. Roll to roll means they are depositing on the molybdenum substrate or the polyamide substrate. So now same company we have divided into the like substrate wise. So rigid substrate is the glass. So these many companies which work on that, now most of them are merged to, or some have company has bought by some Chinese company. And then flexible solar cell, stainless steel, copper, aluminum. So so these stainless steel, copper, aluminum, they are not into the market now. Only the polyamide is there, which the Flisson in Switzerland. Professor Ian Tiwari is from PhD from IIT Delhi. Now is owning this company, Flisson. Ascent Solar is also working on that. So I will skip this like sodium. So till when they have the efficiency around 20%, after that, like they have discovered like post deposition alkali metal, it has increased to 22 to 23%. So now the structure is basically like you use the polyamide, then you deposit the moly at low temperature, CIGS at a low temperature less than maybe around 450. Then they deposit sequentially the sodium fluoride or the potassium fluoride to have some alkali metal. Then they do the post-deposition treatment. And then finally you have the anti-material cadmium sulfide and the transparent conducting oxide. So from 2016 onward, like this is the proposed structure. Like if somebody wants to work on this, this is giving the best efficiency. If somebody wants to change, they can change, but till now this is giving the best efficiency. Like if you have the moly, then you have the CIGS of moly, sulfur selenide, generally some layer is formed during this reaction. And then you have CIGS, then you have post-deposition of certain alkali metal, and then you have CDS and then zinc oxide. And then there is intrinsic zinc oxide is also doped here to avoid any shunting from this top layer to the other. Like if you have certain pinholes, there may be possible of shunting. So people are trying to have and zinc oxide less than 100 nanometers so that you have a turning type of effect. So these are some advantages. I will just skip this. So recently, if you see, so these are the solar cell which these companies which are surviving. Han Energy is Chinese, which has bought this global solar energy, and some other companies. So Han Energy is going on a big way. Okay, this is it was supposed to be there in China by 2020. I was not aware like if it has started or not. So challenges for this area is standardization of equipment for the growth of CIGS absorber film. More than 20% already achieved with single junction, 25% possible in the future. Higher module efficiency. Columnar CIGS structure deposited by alternative process for high efficiency cells and modules. Thinner absorber layer, less than 1 micron, people are trying to work. CIGS absorber film stoichiometry uniformity over large area, because stoichiometry and uniformity is a key concern when you are depositing on the large area, because you have told you like copper should not go more than 20-24%. And similarly, if you are replacing indium to gallium, it should not be more than 20-26. So it should be uniform throughout the area. So then there was concern about the indium. Like if you are going for a large terawatt, gigawatt, so indium ability will be gigawatt, there is no problem. When you're going for terawatt, then there is a problem. Okay, so people are trying to replace the indium. So people are trying to look for other alternative like zinc and tin, which is earth abundant. We were also trying to look for ultra thin solar cells, but practically it is difficult. Like lab scale, it is possible, but like if you go on for large production, then there is a difficulty. So if you can see, these are certain CIGS module people have used for large area production, and then their application. Now we'll just take 5 minutes to just to work on the casterite alternative. So now people are trying to replace, it's the same structure as CIGS. Only thing people are trying to replace indium gallium by zinc tin. The zinc is 20,000 times more abundant than indium. Tin is 500 times more abundant than indium. So they are similar but not the same. So still deep knowledge of material properties are required. Process better suited for casterite. Better contact material. Second, one has to avoid a secondary phase. A lot of secondary phases form in this. That is why it is limited. Structure-wise, again, you see glass. Then you have the molybdenum contact. Then you have this absorber layer. On top of that, you have the cadmium sulfide, and then so same structure. Only the efficiency-wise lab scale is 12.6. So I have some like there are 3 variants. One is the copper zinc tin sulfide. So in this case, like different methods are used, and solution base has given 9.24, and that is in 2015. So let's say now it's nearly 5 years, efficiency has not increased. That is on the lab scale, production chhod dijiye. The other variant is copper zinc tin selenide. Here again, cooperation has given 11.6, and that is again in the 2014, I think, yes, 2014. So now nearly 6 years, efficiency has not increased. And if you have the variation of copper zinc tin sulfur selenium, you are replacing some of the sulfur by selenium. So best efficiency was obtained 12.6 on the small scale, again to 14. And now 6 years, there's no breakthrough. So now people are slowly cutting down on CJTS, because most of the efficiency, like in India's Indian scenario, if you see 5, 6, 7%, and world scenario, it's maximum 9, 8, 9% people are getting, somewhere, sometime 11%. So structure-wise, I will not discuss. This is same as what you have this CIGS. Structure-wise, again same as I told. There is no change. Only problem with these certain binary phases are formed, which is difficult to remove. Okay. So possible reason for the like open circuit voltage deficit, short minority carrier lifetime, high concentration of bulk defects, grain boundaries problem is there, interface defects are also there. Some of them could be related to multi-charge states of tin and volatility of tin chalcogenide species. Tin substitution with other cation is very interesting approach. People are looking for that. Another approach is like they are trying to add some germanium. It has given some increase in the VOC. Okay. So CJTS is basically new emerging technology, long way to go. Still people are finding, I told you like in Indian scenario, like when you get the funding, you get funding for 3 years. Okay, so if you are not able to achieve, so funding is stopped. So next time you look for another material. Perovskite comes, people move to perovskite. Disensitized comes, people try to move disensitized. So there is no consistency. Like that is one of the big problem for developing certain solar cell in India. Okay, so like in the last, I try to conclude. Thin film have the greatest potential for low cost production and will dominate the future of the photovoltaic. Let's see. I like to thank my colleagues and the students who are working on this, and the financial support we get from Ministry of New and Renewable Energy, now DST, that is Center Clean Energy Research Institute have certain fund. Thank you.
Thank you, sir, for a wonderful presentation based on advancement in thin film solar cell. Now the session is open for question, and I think there are few questions in the chat box. First is from the Dr. P.K. Singh. Sir, thank you for such an informative lecture. Now, does any one Indian company which is supplying whole solar cell module?
Which one?
Uh, any Indian company which is supplying whole solar cell module?
Indian company, like in which material?
For whole solar cells module, sir. There is any Indian company which is supplying whole solar cell module?
Which is supplying whole solar cell module are there. Like silicon, there are different companies. Vikram Solar are there. Like CIGS, they have tied up with some German company. They are supplying through that. Cadmium telluride also, like First Solar is supplying through some other partner in India.
Okay, sir. Second question is also from the Dr. P.K. Singh. In CIGS solar cell area for any beginner, what kind of facility must be in the laboratory?
So one is basically you need a thermal evaporation. It depends on like which process you are. If you are using a non-vacuum technique, you should have like some. If you can prepare the nano ink and then you can screen print. That's the one method. If you are using co-evaporation, so one has to have a co-evaporation setup. Like one can deposit 4 materials simultaneously. Otherwise, if you are not having certain fund, then you can have two. So deposit 2 material and then another change the source and then you deposit another 2. So it depends on the funding, what funding you get.
And the third is from Dr. P.K. Singh. In 12.6% record efficiency, what is active area of the solar cell?
Active area is 1 centimeter square.
1 centimeter square.
Because lab scale, we don't work on 1 centimeter square. Again, we divide into smaller area. Then you can say like 1 centimeter square is there.
Yeah.
And the next question is from the Dr. Manish. Yes, sir.
First of all, thank you, sir, for your nice talk. Sir, I have a question. Actually, in case of solar cell, it's a costly experimental techniques needs in the solar cell. The cost is an issue. So can we do some simulation type of work before the experiment to reduce the cost or may approach the best material through the simulation work?
Then simulation people are doing, like people are doing through SCAPS software or the TCAD software.
Yeah.
But experimental and people are proposing, like said the CIGS bilayer, we are double grading, you can propose like this much, but experimentally it is not achievable. There are a lot of difficulty comes when you go from simulation to the experimental.
Sir, have you done any simulation work before your experiment?
No. I am pure experimentalist, but during this lockdown, we have started some work on simulation, but still not published.
Okay.
Because
Okay, sir.
lockdown was all the experiment facilities were closed, so we have moved to some simulation because you need some publication for the student also, like they have to complete PhD.
Sir, actually, the thing is reverse for us. We have published in the lockdown some simulation work, but we need to some experiments. So I will mail you and discuss with you the things.
Yeah, sure, no problem.
Yeah,
we can
thank
always
you,
help.
Thanks a lot, sir. Thank you, sir.
Sir, if there is no more question, one question from my side. Sir, there is any toxicity issue with cadmium in solar cell?
Cadmium as alone is a toxic material, but when it is a compound, then there is no problem.
There is no problem.
Okay.
Okay.
India mein kya hai, like if you have like if you are depositing cadmium sulfide,
yes.
What people are doing, they are throwing into the sink.
Yes.
But if you go abroad and if you work there, they have a different disposable. Like if you have used, you dispose into this. Their safety department will take and then they will take care. India has a big problem. Na? If you see in the school also, if you are using some acid, why you are throwing into the sink only. It's going into the groundwater. So a lot of problems there. Some safety issues still not there.
Okay, sir. So again, I personally feel very honored and happy to thank you, sir. Also my senior and Guru Bhai for such a nice talk and accepting our invitation in this conference. Once again, on behalf of the organized committee and ARST College, I thank you for joining us and introduce us with the recent advances in the field of solar cell. Thank you, sir, for a wonderful
Okay,
talk.
thank you.
And
Thank
Thank
you,
you, sir.
Anil.
Thank you.
thank you.
Thank you, Dr. Manish.
Thank you, sir. Thank you so much, sir. I
I will
think,
Now,
take leave.
yeah, yes,
yes,
sir.
sir.
Thank you. Sure. Thank you, sir. I think, Dr. Arvind, our next speaker is Dr. Ajit Kumar, and he has already joined. Dr. Ajit is there.
One second. Yes.
Yeah. Oh, thank you. Welcome, sir. Uh,
Yeah.
First of all, I want to introduce Dr. Ajit. He is my friend also. Dr. Ajit, presently working as an international research professor at Yenyang University, South Korea since 2018. He has completed his PhD degree in physics from University of Hyderabad. He has worked in various national and international laboratories during his research career. He has published more than 30 research papers in international journals of repute, published book chapters in many books and patents. He has also involved in many ongoing research projects. He is an active member of many active research societies and also awarded with many research honors in international or national conferences. His present research area on ceramic materials and its processing for future technology. Sir, I welcome you in this conference and request you for your talk on the topic aerosol deposited thick films with highly stable energy efficiency for energy storage application. Dr. Ajit.
Yeah. Thank you, Dr. Manish Kumar, for a nice introduction. So uh, maybe this is lunchtime there, but here in Korea it's evening, so it's
Yeah.
good for me. I have good energy to talk. Yeah.
Yeah. Right.
So I'm going to share my screen now. One second. All, are you able to see my screen now?
Uh,
No?
Till now.
Yeah. Maybe now. Now it's okay.
Not now. Yeah. Yeah.
Yeah.
Now okay.
Now it's fine.
Yes.
Okay. So yeah. So good afternoon to all. This is Dr. Ajit from Yungnam University. So the topic of my talk is aerosol depositor thick film for highly stable energy storage applications. So yeah. So outline of the talk is first I'm going to give some introduction about energy storage, like basic to advanced, and then how to fabricate the thick films, and then I'll go to present some of my results. So in the first introduction, I can say energy is a need of every human being, and as we can see that we need energy daily life, and that the energy is the main key factor of the humans to evaluate. So when the human consumes more and more energy, they are considered to be more advanced. So this is the basic difference between the developed and developing nations and the poor nations. The developed nation, they like use more and more energy. So one thing is to produce energy, to generate energy. Second thing is the energy storage. So there are the several example of energy storage, like from our day-to-day use in like a batteries, we can have some energy stored in the form of electrochemical energy, and there are some other examples like now people like now we we generate the energy from our turbines and our power plant. Now at the present time there is a need to store if we have like surplus energy, so there is a need to store energy in big batteries. So we can see here in the South Australia, this is a very famous but Tesla big battery plant. There they have combined like a lot of batteries, and that area is also very big. So for that we need some special kind of materials. So we are going to discuss about that. So for the energy storage application and for the energy storage, that first basic example is a capacitor. That capacitor, what is the capacitor? As we know that metal plates can store the charge, and that we can increase the capacity by just putting a dielectric material or electroceramics, any type of material that have some permittivity. That storage can be enhanced by permittivity times. So there is different type of substance and ceramic, different type of materials. Their relative permittivity is listed here. So there is some, as we can see that there is some special type of material, like it's some electroceramics or dielectric materials. They have high permittivity, so that they can be used to store more and more charge. So this is just example of multi-layer capacitor. This, like electroceramics, can be used as a multi-layer capacitors. So in this multi-layer capacitor, we use for electronics applications, different type of electrical applications. But the main use of this multi-layer capacitor is the storage of energy. So when we use that electroceramics, and when we are able to make device based on that electroceramics, so there is several applications where we can use this type of energy storage, like using this one. So the general example is our mobile phone or like laptop battery, and there are some advanced applications where we can use our material like electroceramics materials. So, but there is some limitations. We cannot use it effectively. There is some limitation for day-to-day use or for commercial applications. Their power density of the electroceramic based capacitor, their power density is very high compared to electrochemical capacitors or their like batteries. But the main disadvantage is their energy density. Their energy density is very low. So use in in the like future type of application, what we need to increase their energy storage density. To increase the energy storage density, there is three, we can say, primary, we have parameters. We can increase first their breakdown field, or we can increase the electric constant or their polarization, and we can decrease the loss. So these two or three main parameters, if we are able to achieve, we can increase their energy storage density or can be used in advanced applications. So there is various mechanism to increase the energy storage or energy density of the ceramic materials. So like we can we divide total up to 5 categories. So the third one, this second and fourth, there are glass ceramic or glass ceramic composites or polymer or ceramic composites. So in this type of in this type of material state, we have high breakdown field. Like we can apply high and high voltage. If we can apply high voltage, like more and more voltage, their storage will be high. But the main problem is when we use the glass ceramic state ferroelectrics, their permittivity is low. So their poration also is low. And the polymer state, as we know that polymer thermal stability is very less compared to ceramic, normal ceramic. So what we can take from what we can do in future, we can use that ferroelectric ceramic electroceramics, and we can reduce down their thickness, and we can make thin and thick film based devices, energy storage devices, so their energy storage density can be enhanced. So for commercial application, what we need high energy storage density, high efficiency, and thermal stability. And what we don't need pollution fatigue and mechanical fatigue. So we are going to increase the energy storage density. We will select some material, and we will apply some special type of fabrication process, and we'll try to increase the energy storage density, efficiency, and thermal stability. So the electroceramics, mostly, as we all know, they have like a special type of some material. Like we can classify them in ferroelectric Fe and relaxer ferroelectric RFE and anti-ferroelectric AFE. So without this, as we know that ferroelectric, relaxer ferroelectric, anti-ferroelectric, these are a special type of materials and they have their domains structure. So based on their domains and nanodomains or their special type of domains, their poration loop is different. Like for ferroelectric, it is square type. For relaxer ferroelectric, it is slim type P loop, and for anti-ferroelectric, it is like double hysteresis loop. So based on that, and for linear dielectric normal capacitor, there is like simple, uh, like we can say very low hysteresis loop, and their poration is low compared to all this ferroelectric and relaxer ferroelectric, all these electroceramics. So how to use them in a energy storage, these materials? So we have two process. One is charging process, one is discharging process. When we apply the high voltage or electric field to them, so their domains are aligned in the direction of electric field. So charge is stored. Then we discharge them, their domains are again randomly aligned. So these are the two equations, the two important equation to calculate the energy storage density. So this W recoverable, WREC as it is written, it's like a green area. This is green area, so it is like uh, the stored energy, and that red area is like loss. So to increase that energy storage, like that, again one more parameter is a eta. This is efficiency. This is divided by storage and storage plus loss. So to increase the efficiency, we need high efficiency. We need to increase the storage density and decrease the loss. So for that, there is, if we use linear dielectric, ferroelectric, relaxer, there is a, for some case, like ferroelectric has high loss but low energy storage. Relaxer has high storage, low loss. Like based, we have to like based on applications, we can select our material. So for the energy storage applications, like as we can see that linear dielectric, ferroelectric, RFE and anti-ferroelectric. So RFE has uh, low loss. It's in this area, that curve area is low compared to other. So it will provide high efficiency plus high storage density. But in the case of anti-ferroelectric, it's also loss is low and poration is high. It will also provide, but if we can make this anti-ferroelectric like like proper double hysteresis type, so we can enhance that energy storage and we can get the low loss. So there is several method or several doping we can uh, make this anti-ferroelectric loop look like that. So in like in our work, what we have did, we have selected two PLJT composition to study this phenomena for relaxer and anti-relaxer. So that relaxer, why we selected PLJT? Because PLJT, that it's like A side lead and lanthanum and B side zirconium and titanium. So if we can modify, if we can this lanthanum, zirconium, titanium, their ratio will define the composition nature. So there is some particular composition is like a relaxer ferroelectric, and another composition is like anti-ferroelectric, and some other composition is like a ferroelectric. So same PLGT we can get the several composition. So for the RFE, we already studied in that bulk form, and that bulk form also given that highly efficient energy storage, and that anti-ferroelectric material, this composition is doped with manganese to achieve like our plan was to get like a low loss by using that manganese doping, making it more and more hard. So this is when we use this in this bulk, this material as a bulk form, their storage is low and DBS, like their background field is also low. To make, so there's if their background field is low, then its storage density is low. So we can further enhance by making them thin and thin, or in the thin or thick film structure. So this is the one slide. There we can see that the dielectric background field is enhanced when we reduce the thickness. So in our case also, what we tried, we have used this material and we have fabricated the thick film by using that aerosol deposition technique. So we can enhance their dielectric background strength and we can increase their storage density. So when we use the bulk ceramic, we can have simple like MIM structure. We have our ceramic palette and just apply the electrodes. We can make like a capacitor structure. And when we use that thin film, this is a cross-sectional view where we have substrate, then electrode, then thick film or thin film. Anything we can use it, or by several methods we can deposit, then again electrodes. So for to like deposit the thick film, so there is several methods we can use it, but I have used, like in our case we have used that aerosol deposition techniques. So there is several methods that they are good for thin film deposition. We can make like thick film, but still that property we can say there is some disadvantage, like pulse laser deposition. This is good for uniform thin films but for small area. When we use the pulse laser deposition, their growth rate is low and it will take long time to deposit, several micrometer if you need several micrometer, and it will the deposition temperature is also higher, 700 800 depend on material to material. And the spin coating technique also, when we deposit it, there like several times we have to deposit, and every time like 50 to some 20 nanometer, 50 or and if we want to make like 2 micrometer or 4 micrometer thick film, it will take like very long time. And we can use the sputtering technique also. If somebody used, they are also aware that it will take long time to make some several nanometer several hundred nanometer thin film. So these techniques are good, but there are several disadvantages. So we can move to some other techniques that will give like more and more like very fast thick film deposition. So this is a one example when we do the high temperature, like when we do the annealing at high temperature and deposit the film at higher temperature. So this is like one structure, MIM structure, and that it shortened or that structure is failed due to oxygen vacancies. In the case PLD, that we are using oxide ceramics where we are heating at higher temperature and that plume is transferring. So there is some oxygen vacancy if we do at higher temperature, and high conductivity, high leakage current. So to avoid this failure, because of that we cannot apply high voltage. And if we are not able to apply high voltage and our dielectric background field is low, so we cannot increase the high storage density. So better to use that aerosol deposition technique. So in this aerosol deposition technique, we deposit the thick film at room temperature. So like a property may be lower at room temperature, but we can apply high field, or we can again anneal that our thick film at some higher temperature, but it is relatively lower than the PLD and other techniques. Like here 500 to 600 degrees Celsius we can achieve that full like a good quality thick film, but that main advantage is we are depositing at room temperature. So in the aerosol deposition technique, we have two vacuum chambers. So one is the deposition chamber, the top one. That bottom one is the aerosol chamber. So in that uh, bottom one, this is small chamber where we can keep our powder. This is one case we have used that alumina particles. Here we can use for to deposit the PLJT thick films. We can use the PLJT powder, and that compressed air and the PLJT powder both were mixed and they form a aerosol. That aerosol is transferred, that particles will transfer with very high speed, and that speed can be controlled to the substrate. So when we transfer to the substrate, it will form within 1 minute several micrometer thick film. And that time also we can control, and that speed we can control it. That air, how much air we need that all this we can control it. This is done in vacuum, like low vacuum. So this is original, real picture in our lab. We have this deposition chamber and powder chamber. Here we can see it. So what is the advantage of aerosol deposition method? Here you can see bulk ceramics have higher property, and we lower down to thin film for several devices. So we need high temperature. So to but in the case of aerosol deposition, that this need lower temperature because we use that calcined or sintered ceramic powder. It's already have the phase, so we are not worrying about the phase formation. Just we need to deposit the good quality film. So the piezoelectric constant is one second advantage of this technique, that piezoelectric constant or dielectric properties or some other property, ferroelectric properties compared to bulk sample is little lower than bulk, but it's higher than other method, the screen printing method or thin film, some thin film forming techniques like ALD, PLD and sputtering techniques. It's higher than that. So that aerosol deposition technique advantage we can say one is room temperature deposition. That second is that properties are higher than thick, and that it will take very less time. Very we can say 1 minute we can get our desired film thickness. So that in the experimental procedure, that powder first we need to prepare the powder up to calcination. Then that calcine powder, we know that we have the phase pure powder. Then directly we can deposit that powder with the help of air. So as a thick film, there are several parameters we need to control it, and that film can be analyzed and characterized. So when we can move to now results. And that our third section is results. So in this case, if your powder is uh, we can say lead based powder or bismuth based powder or some material, they are volatile. So they in that case we need to calcine the powder with precautions. Usually what we do when when we deal with the bulk ceramics, that we calcine the powder is at 850 degrees Celsius. As all researchers, they do the same. They calcine the powder at lower temperature, 800, 850, but that powder has some impurity peaks, because if we do that higher than 800 degrees Celsius or 850 degrees Celsius, that lead loss will be higher. So to then, because for bulk case, you need to sinter again your ceramic. So in this case, that phase is formed in the time of sintering, not in the time of calcination. Yeah. But in this case, we need high phase pure powder. So this 850 degrees Celsius, first that we have tried that powder that calcined at 850 degrees Celsius, but that films was not good. The property was not good due to that impurity peaks. It was leaking. So we slowly increase the powder temperature, calcination temperature. Yeah, we can see we can have some lead loss, but at the same time we need to obtain the high properties than 850 degrees Celsius. So different type of calcine powder calcine at different temperatures were used, and we found that at 950 degrees Celsius that powder is good. It has still little at 29 degree here, it's not visible, still it has some phase of extra weak, but when we come that calcine at 975 degrees Celsius, it's becoming more and more hard. So that film quality again not good. So we have selected this 950 degrees Celsius as a base powder. So uh, that one more one more special thing with this aerosol deposition technique is that if the particle size maybe in micrometer, some like it's big or several micrometer, maybe several nanometers. When it hit the substrate, they are fractured, and that particle size will be less than 10 nanometer or several tens of nanometer. So what will happen when this fractured? So their properties are they are not they will not show their original nature. They are like if we use the ferroelectric calcine powder, but after deposition they are not ferroelectric. They will not show their ferroelectric properties. So what we need to do, we have to anneal. We at room temperature we have increased their, because we have done this process at room temperature. Their dielectric background state is increased, but their nature is little changed. So their other electrical properties come now decreased. So to increase their electrical property, we need to increase anneal them to grow their grain size. So uh, we check their XRD because we already know this is phase pure, so no problem, and we did not detected any extra peaks. That cross-sectional SEM image that shows that thickness of the film is 2 micrometer. There is no delamination. That film is the adhesivity is very good and it shows very dense film. The right side, that surface SEM image, here we can see like small grains. They if we see from TM, these small grains also is a like we can say combination of several grains. So grain size, average grain, these are a cluster, not we can say grain. So dielectric property, we need to check first their dielectric property, their permittivity. So their dielectric property was measured with frequency, temperature, and electric field. So first we can see in the frequency side, their properties, dielectric properties are almost independent, and the temperature also are almost independent. So this type of independent property with frequency and temperature, these are good for stable energy storage application. So this can be attributed to their mixed type of grain structure, their small grain structure. And to like when we use any material as energy storage, we need to apply high voltage, and we need to apply like charges, discharge, charge it again discharge it, like we you do in the case of our mobile batteries, any batteries, rechargeable batteries. So for that, if it is have high, if it has high loss, so that material can be heated and the property can maybe come down. So we have done this capacitance as a function of electric field. We applied high voltage, and in this loop we can see like one like we can see there is loss is very low, and their tunability is high. So it can be used for high voltage for storage application. And the ferroelectric properties, like we need to check their nature, as I said, that A left side A is as deposited and annealed is right side B. So as deposited, it is not showing relaxer property. This material is a relaxer, but their loop is not relaxer type because their grain size changes to the grain size are very small. When we anneal the thick films, so grain size increase to several nanometer, like increase maybe several times. Still, some grains are small, some grains are big. So because of that, it's giving good film hysteresis loop, so that their nature can be confirmed with their current loops also. As we can see that left side current loop is like not for a relaxer type, and right side is like a completely relaxer. So that's why we need to anneal the film at certain temperature. But at 550 degrees Celsius, it's like lower than other techniques. Like for PLD, we need minimum 700 degrees Celsius to get the thin film. Then finally, we need to check their energy storage property for relaxer ferroelectric thin film, thick film. So check the energy storage property. This material P loop in unipolar direction was measured, and their curve area from like up to curve area, this loss, and as we discussed in introduction, was calculated. A high energy storage density up to 44 was found for this PLJT material. It is highest for this type of PLJT material, and for relaxer. For PLJT, any composition, this is highest 44 for thick film, in the case of thick film. And that we need to check this energy efficiency loop. Here we can see that efficiency is almost stable up to 3000 kV per centimeter. So when we increase the electric field, their loss always increase due to the heat or another process, their domain switching. But here, when we increase that electric field, it's changed only from like first to like lower electric field to high electric field, the 6% change. These are highly ultra high stable property energy efficiency, as we can say. So their mixed type of grain structure is making them like fracture grain structure is making them highly stable. So to check to use any material, any ceramics in a energy storage application, that second thing is most important parameter is temperature. Because when we at that commercial application, we use that capacitor at like environment outside environment, or in some instrument or some equipment, their temperature may be high. So we need to check their temperature properties also. So for commercial application, we need thermally stable electrical property, energy storage. So their P loops are almost stable. This was measured up to 120 degrees Celsius. These are maybe sufficient for high energy storage. Maybe maximum it may reach somewhere maybe 100 to 150. Or outside environment, it may reach maybe 50 to 55 degrees Celsius. So their energy storage, first PE loops was measured to calculate the energy storage. Their remnant poration and maximum poration, they did not change up to 120 degrees Celsius. There is very less changes. And that their storage property, as we can see that most important is energy efficiency. Their energy efficiency is approximately 80% from 25 degrees Celsius to 125 degrees Celsius. That change is approximately 4%. So this material, that relaxer ferroelectric, this composition with aerosol deposition, it's found to be electric field stable and temperature stable. So this is good for some high temperature energy storage applications. So we are trying to fabricate some device based on that, and maybe some other application we are planning now. So this material property was compared with the this different type of material, like with different nature, ferroelectric nature, anti-ferroelectric nature, with this PLJT material. So we found, like with comparison, we found that this material shows high efficiency, and material shows high dielectric background field, and their this storage density approximately 44, and that processing temperature is lower than another techniques. These are the thick films, thick films examples. So that same in that same process, anti-ferroelectric material was also measured with the manganese. Manganese was doped, and we with the manganese doping and aerosol deposition. These are thick film with aerosol deposition. That manganese doped shows that higher dielectric properties. So for ferroelectric property, as I said that this this aerosol deposition can change the nature of the material. So previously that relaxer ferroelectric as deposited material, it did not show any relaxer property. When we annealed at 550 degrees Celsius, then it started to show that relaxer property. The same in the case of anti-ferroelectric materials. So here we have one Mn 0% and Mn 1%. So in the both case, this loop is look like relaxer, not anti-ferroelectric. So as we can see that as deposited material also is not that nature of the material, that anti-ferroelectric material is changed from uh, anti-ferroelectric to relaxer type. But this may be due to their small grain sizes, because that grain sizes are fractured into small sizes, nanoscale. We anneal the film at 550 degrees Celsius, but the temperature is not sufficient to show them their original anti-ferroelectric behavior. So if we increase the temperature 600 to maybe 700 or maybe 650 degrees Celsius, they may show. But the problem is when we increase the temperature more than that, that substrate, we are using platinum silicon, it maybe 700, more than 700, there remain this films are delaminated from the substrate. So from here what we can get it, we got that higher efficiency in the case of anti-ferroelectric materials, and this is due to their ferroelectric phase, or their small size of grains is more in AD thick films. So energy storage property for without manganese and with manganese, this special composition, that 780 to 18, this was also measured, and we found that with the use of aerosol deposition, that they have the higher breakdown field, they have high efficiency, and they have high energy storage density. So at last, in the summary, we can say this Lexer ferroelectric and T-ferroelectric materials of PLJT composition was selected to study the aerosol deposition thick film, and their this energy storage density was for Lexer ferroelectric is stable as function of electric field and as a function of temperature, and both show that the high dielectric breakdown steel field up to 3000 kV per centimeter, and these materials can be used for high temperature energy storage applications. Thank you for kind
Thank you,
attention.
Dr. Ajit, for this such a nice talk. And really, it's a need of society. So energy storage is a need of society, actually. We have one or two questions. One from Dr. Kalyani. Uh, she's asking, did you calculate thermal stability? If yes, how?
Yeah, we calculated the thermal stability as I shown that, like uh, like I will share maybe again one more time slide. Yeah, here you need to measure the first PE loops at different temperatures, and that same PE loop can be used to calculate this area, loop area, and that energy storage area, and at different temperature. So we have calculated the efficiency, thermal stability from 25 to, that loop were measured at 25 degree to 125 degrees Celsius. So we can calculate based on this, from this graph we can calculate the energy thermal stability.
Okay, thank you. One question actually I want to ask. Dr. Ajit, you have used, there are number of techniques you have used. What kind of technique may be good for the deposition for the thick films to make a good storage device?
So previously I have used like all these mentioned techniques like PLD and sputtering and sol gel. I have used these techniques. When I came here, I have found that aerosol deposition people are using here more. So that aerosol deposition technique is good to make a thick film, like because it's room temperature deposition, and we can make the flexible devices, like we can deposit in flexible sub capacitor.
One thing more, is there any material that you have synthesized and converted into the device till now?
Yeah, this is like we have just started this work and we published this work now, and our next aim is to make a devices. We have successfully done as a like we can say uh, till now some work we have done, but not publishable or not we can say
Okay, okay. No
up to
problem.
that level. Yeah.
Thank you, Dr. Ajit, for such a nice talk on energy storage. Really, it's a need. And if there is no question, then we are very fortunate that you have accepted our invitation, and we are very thankful to you. Thank you.
Yeah, thank you for the invitation. Yeah, thank you.
Actually, I have an announcement for the next sessions. I I will share the screen for the both the sessions. Is it visible, Amit? Dr. Amit?
Sir, it is
Yes,
okay.
it's visible.
Yeah. The next actually next session is I think there only 15 minutes are left. So the next session is divided into two parts. 18 plus 18 oral presentations. The schedule is completely packed. Yeah, one session will be parallel with this Zoom link, and although again we have given the ID, the session chair will for the 2A session chair persons are Dr. Avnish Pratap Singh and Dr. Raghavendra. Will continue with the OT1 to OT18, and the parallel session 2B will be on Google Meet link, and you will join with session chair Dr. Anjali Sharma and Dr. Yogesh Kumar, OT19 to OT36. Please, one thing is important. You have 8 plus 2 minutes, 8 minutes for presentation and two minutes for the question answer session. So please be bind up your oral talk within 8 plus 2 minutes. Thank you. We will meet in the next session. Thank you.
We will join at 2 sharp.
Yes, yeah, sure. We will join at sharp 2. Okay. Thank you.
The same link, you have to use it.
Yeah, okay.
End कर दूं?
Yeah, yeah.